The 17th of April, 2025. A team working with the James Webb Space Telescope turns its attention toward a faint red star, more than 124 light-years away, and watches a distant planet, K2-18b, drift slowly across the star's face. For a brief window of time, starlight filters through that planet's atmosphere, thin and delicate, like breath passing through fabric. Webb does not capture an image. It captures a spectrum, a ladder of missing colors, where every gap corresponds to a specific molecule. One of those gaps is why the story began to spread. Dimethyl Sulfide, DMS. On Earth, DMS is a familiar chemical signature of life. It rises from coastlines and plankton-rich seas, produced almost exclusively by living marine organisms, microscopic life that grows, reproduces, dies, and releases this gas into the air. And DMS does not last. Sunlight and atmospheric chemistry destroy it quickly. If it appears in large amounts, something must be creating it continuously. What Webb reported was not a declaration. It was not a discovery carved in stone. The signal reached a level known as 3 sigma, roughly a 99.7% confidence that the feature is real rather than random noise. In science, those final fractions matter. This was enough to suggest a door had cracked open, not enough to say what lay beyond it. To even begin to answer what that faint chemical shadow might mean, we have to step back from that single planet and ask a quieter, larger question. What kind of universe produces worlds like this often enough that one of them might, just might, breathe? The working hypothesis is simple, almost radical in its calmness. Life is not an exception. In a cosmos with uncountable galaxies, each holding uncountable stars, it would be stranger if life had happened only once, on one small world, around one ordinary star. The idea here is not that visitors are slipping through our clouds in secret, nor that civilizations are broadcasting obvious messages that we have somehow missed. The starting point is softer, but more far-reaching. Given the raw materials and the laws of physics, life is a normal outcome, not a miraculous glitch. For a long time, this was just a philosophical stance. We had one known example of life, here, and no evidence of planets around other suns. The night sky looked rich, but sterile. The imagination could fill in planets around those distant points of light, but the data said nothing either way. Then, on an October morning in the mid-1990s, that changed. On October 6, 1995, two astronomers, Michel Mayor and Didier Queloz, stood before their colleagues and announced that they had seen the gravitational tug of a planet orbiting a star called 51 Pegasi. It was the first time anyone had confirmed a planet around a star like the Sunday. They had not seen the planet directly. They had measured the star's tiny, rhythmic wobble, starlight shifting back and forth as if the star were breathing in time with an unseen companion. The world they revealed did not fit the comfortable picture many had carried. It was a giant planet, roughly the size of Jupiter or Saturn, but compressed into an orbit far closer to its star than Mercury is to ours, whipping around in just a few days. A hot Jupiter, parked against the furnace. The details were shocking, but the deeper shock was that the barrier had been broken at all. Planets around other stars moved from speculation into the column of reality. The discovery would eventually be recognized with a Nobel Prize in Physics in the year 2019, but its real legacy is not the award. It is the aftershock. Once one such world appears in the data, it is hard to believe it is the only one. What followed was not a trickle, but a flood. Over the next decades, different techniques, different telescopes, and different teams of scientists would push the numbers from one confirmed world to dozens, then hundreds, then many thousands. Some were big and blisteringly hot, some small and dense, some in orbits stretched like ellipses, others locked in tidy, resonant chains. Each new catalog told the same underlying story. If you look for planets, you find them. They are not rare jewels, they are the default byproduct of star formation. Disks of gas and dust around young stars collapse into worlds as naturally as rain condenses out of clouds. That shift matters for our hypothesis. If planets are common, then the first term in the chain of requirements for life is not a bottleneck. The cosmos builds worlds easily. In 1961, at an observatory in Green Bank in West Virginia, an astronomer named Frank Drake wrote down a simple equation on a blackboard before a small group of colleagues. It was never meant to be a magic formula that spits out the number of communicating civilizations in the galaxy. It was more of a checklist, a way to force people to say out loud what had previously been left in a vague cloud of mystery. How many stars form each year in the Milky Way? What fraction of those stars have planets? Around how many of those planets do conditions allow liquid water? On how many of those does life arise at all? On how many worlds does life become intelligent, build technology, choose to broadcast, and continue doing so for a long time? The Drake equation is less a calculator than a chain of questions, each link depending on the one before it. In the early 1960s, most of those entries were complete guesses. The first terms, the ones about planets and habitable conditions, were essentially blank. No one knew how many worlds might exist, or how often they would sit in the temperate zones around their stars. Today, those early parts of the chain are no longer empty. Space missions like Kepler and TESS have spent years staring at patches of sky, watching for the tiny, periodic dimming that occurs when a planet crosses in front of its star, and from those patient stares we now know that planets are not just common, they may even outnumber the stars themselves. A significant fraction of stars, perhaps most of them, sit at the centers of planetary systems, and among those systems, small, rocky worlds are not rare outliers but frequent outcomes. With the James Webb Space Telescope added to that story, we have begun to move beyond simple counts into measurements of temperatures, atmospheres, and chemistry, the very quantities that feed into the middle terms of Drake's chain. The universe seems extremely efficient at building not only planets, but potential homes. The later terms in Drake's chain remain hazier. We still do not know how often life actually emerges when given a suitable environment, nor how frequently it climbs the ladder to complex technological forms. But the equation has already done its job. It has forced us to admit that the question, "Are we alone?" is not one question but many smaller, sharper ones. The first of those now has an answer tilted heavily toward abundance. Before the telescopes caught up, fiction stepped into the gap. In the late 1990s, the film Contact took Carl Sagan's novel and turned it into images. A sudden radio signal from beyond the solar system, a repeating pattern that could not be explained away as noise. At the time, the idea of a call from the universe still hung in an empty sky. We had not yet seen with certainty how crowded that sky was with planets. Yet the film lodged a picture in the shared imagination. A message, carried on waves of light or radio, that says simply, "You are not alone." Reality has unfolded in a quieter way. Instead of a single shout, we have found countless mute worlds. Instead of one clear signal, we have spectra, statistics, and subtle curves in starlight. But those are not as emotionally flat as they sound. They are what you would expect to see in a universe where life is normal, spread over many worlds, but most of it never builds radios or megastructures. If the cosmos is full of microbial oceans and forests of simple life, its voice would be chemical rather than technological. To see why the hypothesis that life is common is not reckless, it helps to play a simple mental game with the numbers, even if we never write them as symbols. Imagine you take a large sample of stars, perhaps 100 of them. Suppose only a modest fraction, say 1 in 10, hosts an Earth-like planet in terms of size and temperature, something with a rocky surface and the possibility of liquid water. That would give you 10 potentially habitable worlds in that small sample. Now imagine that life is not inevitable, even under good conditions. Perhaps only one of those 10 ever manages to cross the bridge from chemistry to biology. In that deliberately pessimistic scenario, One star out of 100 still carries a living world. Now scale that picture up to a galaxy with hundreds of billions of stars. Suddenly, even with conservative assumptions, you are no longer talking about one or two rare oases. You are looking at millions of worlds, where some form of metabolism might be at work. Many of those planets would be lost in the glare of their stars, invisible to us except as tiny dips in brightness or faint smudges of infrared. But in principle, each one is a dim blue dot, or a dim green one, or a world under orange skies, exhaling gases into space. The real universe is even kinder to this line of thought, because the inputs to the game are not arbitrary. We know that water is not a special local ingredient. Telescopes have seen it in the disks around young stars, in the vapor of comets, in the atmospheres of giant planets, and in the cold darkness between stars. Simple organic molecules form on dust grains and in interstellar clouds. Meteorites that fall to Earth carry amino acids, sugars, and other building blocks. The ingredients needed to assemble living chemistry are not confined to Earth. They are woven through the fabric of star and planet formation. We also know that energy sources other than direct sunlight can support ecosystems. On the floor of Earth's oceans, far from the reach of the sun, hydrothermal vents pump out mineral-rich water. Around them, bacteria and more complex organisms build communities powered by chemical gradients rather than light. In caves, in ice, in acidic pools, life finds ways to maintain itself in conditions that would once have been dismissed as sterile. Each example widens the range of environments we can imagine as potential homes. Put these threads together, and the hypothesis that the universe favors life begins to look less like wishful thinking and more like the simplest model that fits the data. Star formation is prolific. Planet formation is efficient. Water and organics are ubiquitous. Energy gradients arise wherever rocks, liquids, and atmospheres interact. The line from physics to chemistry to biology does not require miracles, only time and opportunity. None of this guarantees that any specific world beyond Earth is alive. It does not tell us whether a particular spectrum from a particular planet carries the breath of microbes or the signature of unremarkable geology. What it does is set a prior expectation. When we look at a world in a star's habitable zone and see an atmosphere rich in interesting molecules, the idea that life might be involved is not a wild leap across a chasm. It is one branch on a tree of possibilities that already leans toward growth. This is why the question that hovers over that 3 sigma signal matters so much. It is not just about one gas on one planet, seen by one telescope. It is about whether our broader suspicion is right, that given enough stars, enough planets, and enough time, the universe will repeatedly cross the threshold into biology. If life truly is normal, then the first confirmed hint of it elsewhere is not an isolated miracle. It is a sign that the pattern holds. But patterns have to start somewhere. Every forest began with a first seed. On Earth, that seed was a particular combination of molecules in a particular environment, somewhere on a young planet 4 billion years ago, drifting from simple reaction to self-sustaining chemistry. If the universe really favors life, then that kind of seed should not be unique. It should appear wherever conditions are similar, perhaps in countless versions. The question that follows is uncomfortable and beautiful at once. Did that first seed appear only here, on this small world that learned to name itself? Or has the universe been sowing such seeds everywhere from the beginning, scattering them across the dark in numbers we can barely imagine? If there are seeds scattered through the dark, then somewhere there has to be a first sprout, a moment when dead chemistry quietly crosses a line and does something it has never done before. It begins to make copies of itself. To understand how that can happen, it helps to wind the clock of our own planet back until it becomes almost unrecognizable. Early Earth was not a blue marble under gentle clouds. It was a world of restless crust and raw sky. Volcanoes punching through the surface, pouring out lava and gases, lightning stitching across thick clouds, an atmosphere rich in carbon dioxide, methane, ammonia, water vapor, and other simple compounds. There were oceans, but no forests around them, no animals along the shorelines, no oxygen to breathe. If you could stand there and somehow survive, the air would sting. The horizon would be smudged with ash. And yet, on the scale of chemistry, this was a planetary laboratory. Everywhere that hot rock met water, reactions would have been taking place. Ultraviolet light from a younger, more temperamental sun would have been beating down on the surface, breaking molecules apart and giving them chances to recombine. Lightning would have snaked through the clouds, injecting bursts of energy into the gases above. In deep pools, tidal flats, and steaming vents, countless tiny experiments ran in parallel, over and over, for millions of years. Out of that chaos, something began to happen that could eventually be called life. In the early 1950s, two scientists, Stanley Miller and Harold Urey, tried to see whether some of that planetary-scale chemistry could be coaxed into a glass apparatus. They filled a sealed system with gases meant to mimic what they thought early Earth's atmosphere might have been like. Water vapor, methane, ammonia. They warmed part of it so water would evaporate and condense, and then, across a small gap, they sparked artificial lightning. For days, they let this tiny, closed world run. The water cycled, the gases flowed, the sparks flashed like storms on fast forward. When they later opened the system and analyzed the contents, the water, once clear, had turned a reddish brown. Within that discolored soup were molecules that had not been there at the start. Amino acids, the small organic building blocks that, chained together, form proteins. No cells had appeared. Nothing that anyone would call an organism existed in that flask. But Miller and Urey had shown something important. Under conditions that were not carefully arranged by a biologist, but simply by physics and chemistry, some of the ingredients associated with life could form naturally. The experiment has been refined and debated for decades. Our picture of the early atmosphere has changed. Some of the exact gas mixtures are now thought to have been different. Later work has repeated the core idea under a variety of conditions. The details continue to evolve, but the fundamental lesson is stubborn. With water, simple gases, and energy, organic molecules appear almost as a matter of course. You do not need a cell to make an amino acid. The universe does not need a guiding hand to begin writing a chemical alphabet. That point is echoed from above, in a very different kind of laboratory. On September 28, 1969, a carbon-rich meteorite fell near the town of Murchison in Australia. Locals collected fragments of the dark stone and passed them along to scientists. When those pieces were examined, they turned out to be crammed with complex organic compounds. There were many different amino acids, including some not commonly used by Earth life, along with other molecules that are part of the machinery of genetics and metabolism. Sugars, nucleobase-like structures, and related species. This rock had formed in the early solar system, far from any ocean or atmosphere. Over long times, in the cold and in the gentle radiation between worlds, chemistry on fine dust and ice had assembled intricate carbon-based molecules. Space itself, in other words, behaves like a slow, patient version of the Miller-Urey apparatus. The building blocks that matter for biology are not only possible on young planets, they are manufactured in the dark and delivered as cargo, raining down on any world that happens to sit in the path of such debris. Taken together, early Earth experiments and meteorites like the Murchison stone sketch out the first part of the path. You start with simple molecules, abundant in space and in planetary atmospheres. Under the right mix of energy and environment, those molecules form more complex organics. Those organics are not yet alive, but they are closer to what life uses. They are like a box of unsorted letters spilled across a table. The next question is what happens when those letters spend enough time in the same places. On the floor of our own oceans, in the late 1970s, a small submersible vessel named Alvin descended along a mid-ocean ridge and found something no one had expected. There, in the darkness, were hydrothermal vents, black smokers pouring out mineral-rich water heated by the planet's interior. Around these chimneys were ecosystems: bacteria, tube worms, clams, strange pale creatures thriving in a place with no sunlight at all. The energy that fed these communities did not come from photosynthesis. It came from chemical gradients, from differences in composition between vent fluids and surrounding seawater. Microorganisms tapped those gradients to drive metabolism, and larger organisms in turn fed on them or formed partnerships with them. In one stroke, the discovery widened our sense of what habitable can mean. A world does not need a bright sky and green continents to support life. It can have a thick crust of ice over an ocean, or a deep, lightless sea shot through with vents, and still host thriving biochemistry. From a planetary point of view, this is a profound relief. If life can find a foothold in deep-sea vents on Earth, then an icy moon with a subsurface ocean and active geology looks less like a dead sphere and more like a plausible host for something living. The same logic applies beyond our system. A planet does not need to be a twin of Earth, with the same atmosphere and the same surface geography, for biology to be possible. It needs places where liquid and solid meet, where there are chemical gradients, where complexity can build across time. Scientists use the word abiogenesis for the long, uncertain set of transitions from non-living chemistry to the first entities we would be willing to call alive. It is not a single event, but a chain. Simple molecules form, then combine into longer chains and polymers. Some of those polymers can store information, others can help reactions along. Eventually, you may arrive at systems where a molecule can encourage copies of itself to form, though imperfectly. With enough time, those imperfect copies can compete, with some forms persisting better than others. At some stage, these reactions become enclosed within droplets or membranes, forming protocells that can grow, divide, and inherit traits. We do not yet know the exact pathways Earth followed. There are multiple plausible routes and likely many dead ends in the tree of possibilities. What matters for our larger question is that none of the steps require anything outside the laws of physics and chemistry as we know them. There are no obvious miracles. Given the right setting, a warm pond, a deep vent, an ice-covered ocean with slow currents and dissolved minerals, simple molecules can, in principle, rearrange themselves into more complex patterns that begin to behave in ways we recognize as biological. One way to think about this is as a decision tree. At the top, you ask, can a planetary system produce a rocky world with liquid water or another suitable solvent and some source of energy? For our own galaxy, the answer appears to be yes, in very many cases. If that answer is yes, you move down to the next question. Can simple organics form in that environment? Meteorites, comets, and laboratory experiments all suggest that, again, the answer is yes. Then you ask, given enough time, can those organics assemble into self-replicating systems? Here, the answer is less certain, but we know at least one path exists, because it happened here. If you run that decision tree not once, but across countless planets and moons, the odds begin to change. Even if the transition from chemistry to biology is rare on any given world, the sample size is enormous. You do not have a handful of dice, you have billions of them. Rare events can become almost guaranteed when the number of trials is high enough. This does not tell you how many living planets there are. It tells you that a universe which frequently sets up the right conditions has many chances to roll the combination we call life. Of course, human culture has not always been content with the slow, emergent picture. Stories and films often bring in deliberate creators. A movie like Prometheus imagines towering engineers seeding life, dissolving themselves into alien rivers so that their molecules can spark new branches of evolution. These narratives are compelling partly because they compress the long, messy history of abiogenesis into a single dramatic choice. A figure leaps from a cliff. A planet awakens. Science does not need such engineers, though it also does not entirely rule out the idea that life's ingredients could travel between worlds. The term panspermia refers to the possibility that microorganisms, or at least hardy organic molecules, might be transferred by rocks and ice flung out by impacts, or by dust drifting between systems. If a meteorite like the Murchison stone can carry complex organics from the early solar system to a farm in Australia, then it is not impossible to imagine material being exchanged between planets or even between nearby stars on long timescales. In that view, the seeds of life are not just sown by local chemistry, but carried on slow, interstellar winds. Whether or not panspermia plays a major role, the core picture remains the same. Planets form. On many of them, water or other solvents are present. Simple molecules assemble into more complex organics through the ordinary operation of chemistry. Energy flows through these systems. In sunlight, in volcanic heat, in vent fluids, in tides. Somewhere along that chain, on at least one world, self-replicating chemistry emerges. That emergence is not guaranteed on any specific planet, but once we know it has happened once, on Earth, it becomes difficult to argue that it could never happen again anywhere else. The early Earth, with its lightning storms, its choking skies, its oceans under a dimmer sun, is both alien and intimately ours. It is the cradle in which our entire biosphere learned to exist. At the same time, it is a proof of concept, a demonstration that a planet with the right mix of ingredients and time can turn dead matter into living networks. When we look outward, toward worlds around other stars or oceans beneath icy crusts in distant systems, we are essentially asking whether the same chain of events has been set up elsewhere. Prebiotic chemistry in labs and meteorites shows that the alphabet of life is easy to write. Deep-sea vents and other extreme ecosystems show that the range of habitable conditions is wider than we once thought. Abiogenesis, however intricate, appears to be a path laid out within the rules of nature, not a one-off violation of them. Put all this together, and the idea that life can emerge in many places begins to feel more reasonable than the claim that it happened only once, on a single planet that orbits a single star, in a universe that seems so eager to experiment. If life is not a one-time accident, if chemistry has shown us it is willing to climb toward biology again and again, then the next natural question is simple and unnerving. Where exactly are all those other experiments being run? For a long time, the only laboratory we could see in detail was our own solar system. We could send probes to Mars and Venus, scan the outer planets, and stare at moons and rings and comets. Beyond that, stars were points of light, steady or flickering, but empty of known worlds. It was possible, in the late 20th century, to be an astronomer and genuinely wonder whether planetary systems like ours were rare. There were theoretical reasons to think disks of dust around young stars should collapse into planets, but no one had ever watched another sun be tugged by another Jupiter. There was room, in that uncertainty, for the suspicion that maybe we were a special case. Then came a night that now feels like the opening scene of a different story. On October 6, 1995, observers gathered to hear Michel Mayor and Didier Queloz explain a set of measurements they had been making of a star in the constellation Pegasus, a star now known as 51 Pegasi. They had watched its spectrum, the fine rainbow of its light, for tiny shifts back and forth. Those shifts meant the star was wobbling, pulled by the gravity of an unseen companion. The pattern was regular, repeating over a matter of days. When they worked through the physics, only one explanation fit. A planet, at least as massive as Jupiter, orbiting so close to the star that its year lasted only about 4 Earth days. This was not the kind of planet most people had expected to find first. In the traditional picture, giant worlds formed far from their stars, as Jupiter and Saturn did in our system. A huge planet huddled right up against a sun-like star, a so-called hot Jupiter, seemed like an oddball. But the oddity was part of the revelation. The details might be strange, but the core fact was undeniable. There was a planet around that star. Before that announcement, many astronomers had been skeptical that the available instruments were precise enough to detect planets around sun-like stars at all. Afterward, the atmosphere changed. If a planet could be found once by measuring such a delicate wobble, then the method could be refined, extended, applied to more stars. Other teams began to reanalyze their data and to mount fresh searches. One detection became a handful, then a growing list. The sheer existence of 51 Pegasi b had flipped a mental switch. Instead of asking, "Can we do this at all?" the community began to ask, "How many more are we missing?" The reversal in perception is hard to overstate. In the span of less than a human generation, exoplanets went from ghost stories to a catalogue. Using the radial velocity technique that first revealed 51 Pegasi b and other methods, astronomers confirmed world after world. Some were gas giants close to their stars, others further out. A few were Neptune-like in mass and size. As the instruments improved and the baselines lengthened, it became clear that the night sky is threaded with planetary systems. What had seemed speculative became routine. Small dips in velocity, tracing planets we would never see directly. Then another technique arrived that changed the scale of the search. If a planet's orbit is lined up just so from our point of view, it will sometimes cross in front of its star and block a small fraction of the starlight. That crossing is called a transit. From the ground, it is very hard to see because the atmosphere and the motion of air cause the star's brightness to shimmer. But above the atmosphere, a patient telescope can stare at thousands of stars at once, looking for the tiniest, regular dimmings. On March 7th, in the year 2009, the Kepler Space Telescope was launched with exactly that task. It was not aimed at a specific star of interest. Instead, it spent years gazing at a single patch of sky, watching and counting. Each time a star dimmed and then brightened again on a strict schedule, the Kepler team could infer the presence of a planet. The size of the drop in light revealed the size of the planet relative to its star. The spacing of the dips told them the orbital period, and from that, given the star's properties, they could estimate how much energy the planet received. The results were almost overwhelming. Kepler found thousands of candidates, later confirmed as planets, ranging from worlds larger than Jupiter down to planets smaller than Earth. By analyzing how many transits occurred among how many stars, and correcting for the fact that only a fraction of planetary systems are lined up in the right way for transits to be visible, astronomers could extrapolate. The conclusion was startling in its simplicity. Planets are common, not just in a casual sense, but in a deep statistical one. It is likely that, on average, there is at least one planet for every star in the galaxy, and quite possibly more. This means that if you could see the Milky Way not as a mist of starlight, but as a map of tiny orbits, nearly every point of light would be surrounded by small circles and ellipses. Our Sun, with its family of worlds, is not an exception. It is an ordinary example of a general rule. Among the Kepler discoveries and follow-up work, there were precious hints of something more specific. Planets close in size to Earth, in orbits where the temperature might allow liquid water at the surface. These are not confirmations of actual oceans, but they are candidates, dots on the map where conditions might be friendly enough for life as we know it. They are the first brushstrokes in an emerging forest of potentially habitable worlds. As Kepler's main mission ended, other instruments took up the search with different strategies. The Transiting Exoplanet Survey Satellite, often shortened to TESS, was launched later, in the year 2018. Instead of staring at one patch of sky, it surveyed almost the entire sky in strips, focusing on relatively bright, nearby stars. The aim was not just to count planets, but to find worlds close enough and around stars bright enough that future telescopes could study them in more detail. While these census missions were running, certain systems stood out and captured the public imagination. On February 22, 2017, astronomers announced that a small, cool star called TRAPPIST-1, about 40 light-years away, hosted at least 7 planets roughly similar to Earth in size. Several of them orbited in the star's temperate zone, where, under the right conditions, liquid water might be stable on their surfaces. Here, at last, was not just a single planet of interest, but an entire compact system, with worlds packed close together, orbiting a dim red sun. For a moment, it felt as if someone had pointed to a real, specific place in the sky and said, "There, that is another system of small rocky planets." The details of TRAPPIST-1 are complex and still being untangled. The star is a red dwarf, active and prone to flares. The planets may be tidally locked, showing the same face to their star. but as a symbol, the system is powerful. It tells us that small stars can host multiple Earth-sized planets, some in the habitable zone. It suggests that such configurations might not be rare. On January 3, 2020, another name joined the list, TOI 700d. This planet, discovered by TESS and confirmed through follow-up observations, orbits a dwarf star roughly 100 light-years away. It is close to Earth in size and sits within the habitable zone of its star, receiving a level of stellar energy not wildly different from what Earth gets from the Sun. Climate models suggest that, given a reasonable atmosphere, its surface temperature could allow liquid water. We do not yet know if that atmosphere exists, nor what it is made of, but the mere fact that such a planet has been identified feels like a signpost. Around the same time, attention turned to some of our very nearest stellar neighbors. In the year 2019, a team analyzing data from ground-based observatories reported planets around a tiny, cool star known as Teegarden's star, only about 12.5 light-years away. Two of these planets, commonly referred to as Teegarden's star B and Teegarden's star C, appeared to lie in or near the star's habitable zone. Their exact properties are still being refined, and rankings of Earth-likeness are always model-dependent, sometimes misleading. But more important than any score is the simple geographic fact: potentially temperate planets exist in our immediate cosmic neighborhood. If you were to stand back and draw a map, placing the Sun at the center and marking every known exoplanet within a few hundred light-years as a tiny glow, the region around us would not look empty. It would resemble a faint, thickening mist, a cloud of possibilities. Some of those lights would be giant planets hugging their stars. Some would be icy worlds far out. But many would be roughly Earth-sized, in orbits where their surfaces could, in principle, host liquid water. Dozens lie within tens to hundreds of light-years. That is far beyond the reach of any spacecraft we can build now, but on the scale of the galaxy, it is next door. Emotionally, this shift is hard to absorb. In less than 3 decades, we have gone from a state where it was plausible to worry that planetary systems might be rare, to a state where we can list specific worlds, with catalog names and measured orbits, that could have oceans, clouds, and weather. We can say, with some confidence, that the typical star does not sit in isolation. It has company. The question is no longer whether there are other planets, but what those planets are actually like. For a while, our tools only allowed us to infer masses, sizes, and orbits. We could tell roughly how big a planet was, how often it circled its star, how close in it sat, and from that, how much light it received. That alone was enough to revolutionize our picture of the galaxy, but it left a deeper curiosity unanswered. Knowing that a planet exists is not the same as knowing whether it has an atmosphere, whether that atmosphere is thick or thin, toxic or breathable, clear or cloudy. It does not tell you whether there is water vapor in the air, whether there are clouds of ice or dust, whether gases like carbon dioxide, methane, or oxygen swirl above the surface. The move from counting planets to reading their environments is a qualitative change. It is the difference between a census and a biography. When you look at that map of nearby candidate worlds, the natural next question is, which of these actually carry the right conditions for life, and how can we possibly find out from so far away? That is where the James Webb Space Telescope enters the story. All of the quiet revolutions that led from 51 Pegasi b to TRAPPIST-1 and TOI 700d set the stage. They gave us a forest of exoplanets and showed us that habitable zones are not empty. They identified nearby systems where the starlight is bright enough, the planets align just right, that a sensitive instrument could do more than detect a dimming. It could use those tiny changes in light to dissect the air of another world. If we can already measure the flicker of a star as a planet crosses its face, what happens when we spread that light out into a spectrum and look for the fingerprints of molecules in it? When you do that, when you stretch a planet's dimming of its star out into a rainbow of missing colors, the light turns into something like a story. Not just that a world is there, but what kind of sky it carries on its shoulders. The basic trick sounds almost too simple. Imagine a star as a perfect, steady bulb. Now put a planet in front of it. Not as a solid disk, but as a circle wrapped in a thin shell of gas. When the planet passes between the star and our telescope, most of the starlight is blocked by the solid bulk, producing the small dip in brightness we call a transit. But a tiny fraction of that light threads its way through the planet's atmosphere along the edges, like sunlight leaking around the rim of a coin. As those rays pass through layers of gas, molecules in the air grab certain colors and let others pass. Each type of molecule has its own pattern of favorite wavelengths, its own bite marks in the spectrum. If you collect that light and spread it out with a prism or a diffraction grating, you no longer see just a smooth band of color. You see a barcode, a ladder of bright and dim stripes. Where the spectrum is unexpectedly faint, something in the atmosphere has been drinking those photons. Hydrogen, water vapor, methane, carbon dioxide, carbon monoxide, sulfur-bearing gases. Each has its own fingerprint. We never see the planet's clouds directly. We do not glimpse waves on any distant sea. But we can hold a list of wavelengths and say, with some confidence, these are the chemicals that must be present to carve this pattern. Long before anyone thought of doing this for exoplanets, astronomers used the same kind of spectral fingerprints to learn what stars are made of. In the 19th century, by examining the dark lines in the sun's spectrum, scientists identified helium as a separate element before it was ever found on Earth. The name comes from Helios, the Sunday. We knew that a new kind of atom was real because of how it interrupted light. The James Webb Space Telescope is essentially extending that same logic outward to places where no physical sample will ever be scooped up and carried back. Light is the sample. Even before Webb, earlier instruments were already pushing toward this kind of atmospheric reading. The Hubble Space Telescope, designed primarily for imaging and ultraviolet and optical work, turned out to have just enough sensitivity at certain infrared wavelengths to glimpse simple signatures in the air of some big exoplanets. In the year 2019, Hubble observations of a planet called K218b suggested the presence of water vapor in its atmosphere. The signal came from transit spectroscopy. The planet crossed its small red star, light filtered through its gas envelope, and the spectrum showed telltale dips where water would be expected to absorb. That result made headlines, because K218b orbits in the habitable zone of its star and is larger than Earth, but much smaller than a typical gas giant. It lives in a category that might, under some models, include ocean worlds with thick atmospheres. But even in that first wave of excitement, the interpretation was complex. Other gases, like methane and nitrogen, were not well constrained. Some models implied a relatively clear atmosphere. Others required clouds or haze. The detection of water vapor was robust, yet what that meant for the actual environment on the planet was already a puzzle. Even with the best tools available at the time, the chemistry of that distant sky could not be pinned down cleanly. Webb was built in part to go beyond those limitations. Its mirror is larger. Its instruments are tuned to the infrared, where many important molecular lines sit, and it operates in a cold, stable environment, far from the heat of Earth. It is not a camera in the ordinary sense, sweeping the sky for pretty pictures. It is more like a set of exquisitely sensitive ears, listening for faint notes in starlight that has passed through alien air. Picture a moment when Webb is tasked with turning that ear toward the small star in the constellation of Leo that hosts K218b. Somewhere beyond Earth's orbit, the telescope sits in steady freefall around the sun, shielded from its heat by a silvered sunshade, floating in a kind of engineered night. The star itself is not dramatic to Webb's instruments, just a soft point of infrared light. But astronomers know that at a certain time, predictable down to minutes, the planet will begin to slide across the star's face. As the transit starts, Webb's detectors begin collecting photons at a steady pace, recording how many arrive at each wavelength. Most of those photons are unaffected by the planet. They come straight from the star. Yet a small subset, those that skirt through the limb of K218b's atmosphere, carry additional information. They have been scattered, absorbed, re-emitted. Some colors are slightly less common in the stream than they would be if the star shone alone. Over hours, as the planet moves in front and then away, the telescope keeps its gaze locked, building up a spectrum that is really a composite picture of that atmosphere from above, 124 light-years away. What comes back is not a crisp photograph but a wavy line on a graph, with bumps and dips. Turning that line into a list of molecules involves a process called retrieval. Scientists start with a model atmosphere, a guess at temperature, pressure, composition, cloud layers, and other properties. They use physics to predict what the spectrum would look like for that atmosphere, then compare it to the data. The difference between the two is used to adjust the model. Repeat enough times, and you can find sets of atmospheric properties that reproduce the observed pattern reasonably well. Crucially, this is not a matter of fitting one parameter. There are many knobs to turn, and some of them can compensate for others. You can mimic the effect of certain molecules by changing cloud height, or adjust temperature profiles to influence how absorption features appear. That means retrieval is inherently probabilistic. Instead of one single answer, you get a range of plausible atmospheres, with some more likely than others given the data. Confidence levels come in shades, not in absolute declarations. This is why it matters that Webb has already shown it can handle simpler cases. Its first exoplanet observations focused on large, hot worlds, where signals are stronger and the details of clouds and hazes matter a little less. For example, Webb turned its spectrographs on a planet known as WSP-39b, a gas giant roughly similar in size to Saturn, but much closer to its star, and therefore extremely hot. Because its atmosphere is puffed up and heavily irradiated, the imprint it leaves on starlight during transit is relatively prominent. In those observations, Webb clearly detected carbon dioxide, one of the main carbon-bearing molecules astronomers expected to see. It also picked up signs of water vapor and even features associated with sulfur dioxide, which suggested that high-energy radiation from the host star was driving photochemical reactions in the planet's upper atmosphere. In another case, a planet called WSP-96b, previously thought to have an almost cloud-free atmosphere, revealed both water vapor and evidence of haze or clouds when Webb observed its transit. These worlds are too hot and too close to their stars to be considered habitable, but they serve as testbeds. The fact that Webb's spectra of them line up with expectations, or sometimes correct earlier misconceptions in coherent ways, builds trust in the instrument and the methods. By working through these easier, louder atmospheres first, scientists learn how Webb behaves, how its detectors respond. Where subtle instrumental signatures might masquerade as real features, they refine the data reduction pipelines, identify sources of noise, and learn how to separate a genuine molecular absorption line from a glitch in the hardware. All of this groundwork matters when the targets are cooler, smaller planets with fainter signals, where every tiny dip in the spectrum will be scrutinized. Against that backdrop, the idea of a biosignature has to be defined carefully. In popular imagination, a biosignature sometimes sounds like a direct message, a wave from a distant shore. In reality, it is a pattern in the chemistry of an atmosphere or surface that is very hard to explain without invoking life, or that at least strongly suggests biological processes as one of the most plausible causes. On Earth, for example, the simultaneous presence of abundant oxygen and methane in the atmosphere is a strong biosignature because those gases react with each other. Left alone, they would tend to cancel out. Their continued coexistence implies constant replenishment, which here comes largely from photosynthesis and from the metabolism of organisms. Other potential biosignatures are more subtle. A single molecule might be produced by both living and non-living processes, but the relative amounts of several gases together under certain stellar and planetary conditions might point toward life as the most reasonable explanation. In some cases, the absence of expected gases can be telling. The point is that a biosignature is not a photograph of an organism, nor an encoded greeting. It is an imbalance, a chemical disequilibrium that seems to require something more than geology and sunlight to sustain it. The historical analogy to helium in the Sun is tempting but imperfect. When astronomers saw spectral lines they could not match to any known element, they inferred that a new element existed and that it was present in the solar atmosphere. That inference was later confirmed in laboratories. With life, there is no such easy loop. If Webb sees a pattern of gases on a distant planet that looks odd, we cannot go there and sample the air. We can only compare it to models and to what we know from our own world and from theory. The inference, if it comes, will be statistical and circumstantial, not a direct detection in the everyday sense. That built-in ambiguity is amplified by the challenges of the measurements themselves. Transit spectroscopy for small, temperate planets pushes Webb close to the edge of what it can do. The changes in starlight caused by the atmosphere are often a tiny fraction of a percent. Instrumental drifts, tiny temperature changes in the telescope, cosmic ray hits on the detectors, all can introduce signals that, if not corrected, might mimic or hide real features. Assumptions about how clouds form, how aerosols scatter light, and how the star's own spectrum behaves also feed into the retrieval process. Small shifts in those assumptions can produce large changes in the inferred composition. Because of that, any claim about a biosignature gas has to pass through a gauntlet. Is the feature in the spectrum truly there, or is it an artifact of the data reduction? If it is real, can known chemical pathways in a lifeless environment produce the same gas in sufficient quantities? Do clouds, hazes, or temperature inversions offer alternative explanations? Are there other molecules whose presence or absence support or undercut the life-based interpretation? The goal is not to kill excitement, but to ensure that what survives is robust. K218b is emerging as a kind of live case study in how this process works under public scrutiny. It sits in the habitable zone of a small star, with a size and mass suggesting it might be an intermediate type of world. Neither a bare rock nor a full-fledged gas giant. Hubble's detection of water vapor made it an early favorite for more detailed study. Webb's instruments have now taken multiple looks at it during transit, gathering spectra that seem to show not only water but methane and carbon dioxide in a hydrogen-rich atmosphere. Some analyses have hinted at the possible presence of more exotic molecules associated with biological activity on Earth. Other groups, using different modeling choices or treating the noise differently, have been more cautious, finding the general atmospheric picture plausible but not seeing strong support for the more dramatic claims. This back and forth is not a sign that the system is failing. It is how the system is supposed to work when the stakes are high and the data are right at the edge of what is possible. As more observations are collected, as retrieval methods are cross-checked and refined, the picture of K218b's atmosphere will sharpen. It may reveal a consistent story pointing toward a certain range of conditions, or it may remain ambiguous, a reminder that our tools are powerful but not omnipotent. What Webb has already done, even before any verdict on specific molecules, is prove that reading the air of a distant world is not science fiction. It is an ongoing practice. Every spectrum from a hot Jupiter or a puffy Neptune-sized planet validates the method, trains the community, and makes the claim that we could one day identify a true biosignature more credible. We are not just counting worlds anymore. We are, in a limited way, tasting their weather. Now that we can do that, now that a planet's atmosphere can be turned into a line of bumps and valleys on a graph and read for hints of habitability, it makes sense to single out one world in particular. K218b sits in the crosshairs of that effort, a candidate that could be an ocean wrapped in hydrogen skies or a swollen, uninhabitable gas ball. The difference between those pictures lies in the spectra, in the precise depths of lines, in what they whisper about pressure, temperature, and chemistry. To understand why this one planet has become such a focus, we have to open its file and sit with the possibilities it represents. On paper, the file looks almost modest, just another entry in a long list of worlds. But as you read down the columns, the numbers begin to tug at the imagination in a way the others do not. K218b first came to our attention in the middle of the last decade, when the extended K2 mission of the Kepler Space Telescope stared at a patch of sky in the constellation of Leo and noticed a recurring, shallow dip in the light of a small red star. The pattern was regular, repeating every little over a month. Each time, the star dimmed slightly and then recovered, a signature that, by now, astronomers know how to read instinctively as a planet crossing in front of its host. From the depth of that dimming and the properties of the star, they could estimate the planet's size, roughly 2.5 times the radius of Earth. Later measurements of the star's wobble, as it responded to the planet's gravity, suggested a mass around 8 or 9 times that of our home world. Those simple comparisons already place K218b in a curious category. It is larger and heavier than Earth, but far smaller than the ice giants in our own system. It sits in a class often called super-Earths or mini-Neptunes, worlds with no familiar counterpart orbiting our Sunday. If you imagine lining up the planets we know, from small rocky Mercury through Earth and Mars, onward to Neptune and Uranus, K218b would slot uncomfortably into the gap between the rocky and the gaseous, between the places where you can stand and the places where you would fall endlessly through layered clouds. Its orbit adds another layer of interest. K218, the star, is a cool red dwarf, dimmer and smaller than the Sunday. Yet K218b circles close enough that, over the roughly 33 days of its year, it receives a level of energy that, under the right conditions, could yield temperatures not wildly different from those on Earth. It is neither roasted the way a hot Jupiter is, nor left in deep freeze far from its primary. Calculations of the balance between incoming starlight and outgoing planetary heat place it in what astronomers call the habitable zone. The range of orbits where, assuming a suitable atmosphere, liquid water might be stable at the surface. That phrase, habitable zone, can easily be misunderstood. It does not guarantee habitability. It does not promise oceans or rain or coastlines. It is a geometric and energetic statement. At that distance from that type of star, a planet could, in principle, have surface temperatures that allow water to be liquid, given the right greenhouse effect and albedo. Even so, for K218b, the placement is strikingly comfortable. Follow-up observations refined its orbit, tightened the estimate of how much energy it absorbs, and confirmed that it is neither just inside the inner edge of that zone, nor just grazing the outer rim. It sits in a space many have lazily nicknamed Goldilocks, not too hot, not too cold, at least in the abstract. The abstract, however, is not where life lives. To move beyond orbital diagrams, we have to ask what kind of world could exist with that size and mass at that distance from that star. One possibility, which has captured a great deal of attention, is something called a Hycean world. The term is a blend of hydrogen and ocean. In this picture, K218b would be a planet with a deep global sea, perhaps tens or even hundreds of kilometers thick, overlain by a thick atmosphere dominated by hydrogen and helium, with other gases mixed in. The pressure and temperature at the interface between that atmosphere and the ocean would depend delicately on the total mass of the air, the amount of greenhouse warming, and the energy received from the star. If those parameters fall into certain ranges, the scenario becomes enticing. A hydrogen-rich atmosphere is efficient at trapping heat. So even around a relatively dim red dwarf, a planet can maintain temperate conditions below the clouds. The upper layers of the air might be cold and thin, but lower down, the temperature could rise to values compatible with liquid water. Under such skies, a vast ocean could remain unfrozen, circulating slowly, exchanging gases and heat with the atmosphere above. There might be no continents, no islands. Nothing resembling the patchwork maps we are used to. Only an endless, restless surface of water. For microbial life, such a world might be surprisingly friendly. On Earth, tiny organisms in the upper layers of the ocean already live in a similar interface, bathed in light, exchanging gases with the air, contributing to cycles of carbon, sulfur, and other elements. In a Hycean world, the specifics would differ: chemical compositions, spectral colors, the balance of radiation, but the general idea could hold. Below the clouds, above the deeper, high-pressure layers of the sea, there might be a band where temperature, pressure, and chemistry allow metabolism, replication, and evolution. The planet's deep interior, perhaps a rocky or icy core, would be hidden far beneath that global ocean, irrelevant to the daily lives of any floating microbial mats or drifting cells. The energy balance that allows this depends on the quiet behavior of the host star and the insulating properties of the atmosphere. Red dwarfs like K2-18 emit a large fraction of their light in the infrared, which hydrogen-dominated atmospheres can absorb efficiently. That means a planet can orbit farther out and still maintain warmth. Or, equivalently, a world at K2-18b's distance can remain temperate even if some heat leaks away. If clouds form at certain altitudes, they can reflect a portion of the incoming starlight back into space, preventing runaway heating, while still allowing infrared trapping below. In climate models, by adjusting the thickness and composition of the atmosphere, scientists can slide the conditions on K2-18b from frigid to boiling. It is within that sliding space that the Hycean hypothesis finds its footing. But for all its appeal, this picture is only one way to arrange the ingredients. The same overall mass and radius could describe a planet with a very different interior structure. Instead of a relatively thin hydrogen envelope over a large ocean atop a dense core, K2-18b might be more like a mini Neptune, a world where hydrogen and helium make up a substantial fraction of the bulk, with only a small rocky core deep inside, crushed by enormous pressures, and with any water present in high-pressure icy phases, rather than as a freely circulating sea. In that case, there would be no clear surface in the familiar sense, no interface where an ocean meets an atmosphere. Density profiles built from the available data allow for both kinds of solutions. This ambiguity arises because measurements of mass and radius, while powerful, do not uniquely determine composition. A planet that is somewhat less massive but more enriched in heavy elements can have the same radius as a more massive planet with a larger fraction of light gases. Trade-offs between rock, water, and hydrogen lead to families of interior models that are compatible with the observations. To break the degeneracy, we need more constraints: atmospheric composition, thermal structure, perhaps hints of tides, rotation, or magnetic fields. Until then, the true nature of K2-18b remains hidden beneath the smooth, deceptively simple numbers. Not everyone in the field is equally enamored of the Hycean framing. Some researchers look at K2-18b's size and mass and argue that a predominantly gaseous interpretation is more natural. They point out that, in planet formation simulations, once a world reaches a certain threshold of mass in a planetary nebula, it tends to accrete large amounts of hydrogen and helium, swelling into something more like Neptune than like Earth. From this perspective, K2-18b may be better thought of as a small gas giant than as a super-Earth. In such a case, any habitable band, if it exists at all, could be confined to very specific layers in the atmosphere, and the stability of such niches over geological time becomes a serious question. Others counter that our own solar system is a poor guide at these intermediate sizes. We have no planets between Earth and Neptune. All of our experience is at the extremes: thin, rocky atmospheres or thick, giant envelopes. Exoplanet surveys, however, show that nature happily fills the gap. Many stars host worlds with sizes similar to K2-18b. The diversity of those planets may be large. Some could be rocky spheres with thick atmospheres. Others could be envelope-dominated mini-giants. Without a local sample to dissect, we are left to argue from theory and from the few atmospheric clues we can gather. As the debate unfolds, it is helpful to borrow a simpler, more visual way of holding both possibilities in mind. Imagine two posters pinned side by side on a wall. On the first poster, K2-18b is painted as an endless ocean under pale, streaked clouds. The star is a small red orb in a hazy sky, its light dim but steady. Waves roll across a planet-wide sea. Somewhere in the upper layers of that water, perhaps in floating colonies or in microscopic free swimmers, chemistry has learned to copy itself. There are no continents to walk on, no mountains to climb, but the planet is alive in a diffuse, global way. On the second poster, the same orbit, the same star, and the same mass are rendered in a different style. The planet is a swollen sphere of gas, with thick, opaque clouds blotting out any notion of a surface. Deep below, pressures climb to values that crush molecules into exotic phases. If there is any kind of ocean, it exists as supercritical fluid or high-pressure ice, layered beneath vast stacks of hydrogen and helium. Temperatures and pressures in the accessible parts of the atmosphere may swing too wildly, or sit too far from any biochemically comfortable range, for life to find a foothold. The world is dynamic, maybe beautiful in its storms, but biologically empty. Both posters are consistent with what we know so far. Both are physically plausible outcomes of planet formation around a red dwarf. What we are trying to do, with telescopes and spectra and careful modeling, is decide which one belongs on the wall, or whether the truth lies somewhere between them, in a configuration our imaginations have not yet fully drawn. The fact that K218b orbits in the habitable zone is part of why these images feel so charged. If it were much closer to its star, the Hycean painting would be harder to justify. The planet would likely be too hot, much farther out. And the mini-Neptune vision would tilt toward a frozen giant. Sitting where it does, receiving a moderate amount of energy, K218b occupies a kind of conceptual crossroads. It is just plausible enough as an ocean world to keep hope alive, and just ambiguous enough as a gas-rich planet to keep skepticism alert. Over the years since its discovery, astronomers have refined the parameters of the system. They have watched multiple transits, measured the timing, checked for hints of additional planets, estimated the star's activity levels, and mapped out the flux of radiation K218b receives. Each new data point tightens the constraints, nudging the models. None of them, however, can by themselves answer the question that pulses at the heart of the file. What does the air around this planet actually contain? And what does that imply about what lies below? That is where Webb enters, not as a background character, but as the instrument that can turn the two posters into testable hypotheses. By using transit spectroscopy to identify molecules in K218b's atmosphere, Webb can tell us whether the air is indeed hydrogen-dominated, whether there is water vapor mixed in, whether methane and carbon dioxide are present in amounts that support or challenge the Hycean idea. It can hint at temperature gradients, cloud decks, and the pressure levels where different absorptions occur. Every one of those clues feeds back into models of the interior. If the spectra line up well with a scenario in which a deep ocean sits beneath a relatively thin hydrogen layer, then the first poster gains weight. The notion of a global sea beneath alien skies becomes less a dream and more a working picture. If, on the other hand, the data demand a much more massive envelope with compositions and temperatures that point toward a mini-Neptune, then the second poster takes precedence and K218b slides toward the side of the ledger where Earth-like biospheres are far less likely. Either way, the planet remains important. A Hycean K218b would be a strong candidate for a new category of potentially habitable worlds, very different from Earth, but welcoming in their own way. A mini-Neptune K218b would serve as a warning about the limits of habitability at certain sizes, reminding us that not every planet in the habitable zone is a viable home. In both cases, the system teaches us something about where to look and how to interpret what we see. All of this, by itself, would be enough to make K218b a compelling target. A planet in the habitable zone of a nearby red dwarf, sitting between Earth and Neptune in mass and radius, with a star quiet enough and bright enough in the infrared for its atmosphere to be probed, is already a rare and valuable opportunity. But what pushed it from interesting to electrifying was not the orbit, nor the size, nor the theoretical possibility of a global ocean. It was what Webb's atmospheric readings seemed to whisper between the lines of water, methane, and carbon dioxide, hinting at something more, and forcing us to ask whether, on this particular world, chemistry alone is enough to explain the story written in its light. It is one thing to argue, in the abstract, that a planet might be an ocean world. It is another to see its light turned into chemistry and feel, for a moment, as if the planet itself is answering. On September 11th, in the year 2023, a team working with data from the James Webb Space Telescope released their first detailed look at the atmosphere of K2-18b. The observations came from Webb's near-infrared instruments, which had watched the planet pass across the face of its small red star and recorded how the starlight changed. When the spectra were assembled, the line that emerged was not flat. It carried hills and valleys at wavelengths where certain molecules are known to bite into the light. In those shapes, the team read the signatures of methane and carbon dioxide, along with a noticeable absence of ammonia. For a world wrapped in hydrogen, that combination is not trivial. In simple, hot, hydrogen-rich atmospheres, ammonia is often expected to be more abundant. Its absence suggests that nitrogen may be tied up in other forms, or that chemistry has driven it downward or broken it apart. At the same time, the presence of methane and carbon dioxide together, in particular ratios, hints at a more complex interplay between deep and shallow layers, between whatever is happening at or below the ocean line and what is being released into the air above. The pattern was exactly the kind of thing that had been predicted for a Hycean planet, where a water-rich sea sits under a hydrogen-dominated sky. The press releases that day were careful. They spoke of carbon-bearing molecules, of a hydrogen-rich atmosphere, of a planet in the habitable zone. They emphasized that K2-18b is unlike anything in our solar system, that its mass and size place it between Earth and Neptune, and that the new data strengthened the case for a possible ocean beneath its clouds. But tucked into the technical notes and mentioned, almost tentatively, in the public statements, was another detail. The spectra contained a small feature that, if interpreted one way, might be a hint of a molecule called dimethyl sulfide. Dimethyl sulfide is not a name most people carry around in their heads. On Earth, however, it plays an outsized role for something you rarely hear about. It is a sulfur-bearing compound produced, as far as we know, almost entirely by life, especially by marine microorganisms. Phytoplankton in the upper layers of the ocean generate precursor molecules that, when broken down, release dimethyl sulfide into the air. Once in the atmosphere, it affects how easily clouds form over the sea. In some regions, it is part of a feedback loop between biology, cloud cover, and climate. If you have ever stood on a rocky coast and smelled a faint, sharp tang on the wind, you have inhaled traces of it. In a poetic sense, it is part of the scent of a living ocean. So, when the Webb team noted that there might, possibly, be a spectral bump consistent with dimethyl sulfide in the atmosphere of K2-18b, ears perked up. They were not claiming a detection. The signal was weak, right at the threshold of what could be trusted, sitting among regions of the spectrum where other uncertainties lurked. In their own language, they stressed that it was a hint that would require more data and careful analysis. But the mere fact that this particular molecule had entered the conversation changed the emotional register of the discussion. Methane and carbon dioxide, by themselves, can be produced by a wide range of processes. Volcanism, photochemistry, serpentinization in the crust, and other abiotic mechanisms can contribute. Life can certainly make them too. And on Earth, living organisms play a major role in maintaining their levels. But they are not uniquely biological. Dimethyl sulfide is different. On our planet, it is so closely tied to marine life that some scientists have long pointed to it as a candidate biosignature gas. Something that, if seen in high abundance elsewhere, under the right conditions, would be very difficult to explain without invoking biology. In the months after that first release, papers and commentaries began to appear, teasing apart what Webb had really seen. The consensus on the solid features was strong. Methane appears to be present at levels higher than would be expected for a simple, cold, hydrogen atmosphere in equilibrium, especially when paired with the detected carbon dioxide and the low ammonia. Together, these support the notion of a water-rich environment underneath, with active chemistry linking the deep layers and the air. The possible dimethyl sulfide bump remained an asterisk, an intriguing but unproven note at the margin of the page. Still, the idea took hold, not as a conclusion, but as a question. If further observations were to firm up that spectral feature, what would it mean? Could there be non-biological pathways in a hydrogen-dominated, ocean-covered world that produce dimethyl sulfide in quantities sufficient to imprint the spectrum? Would exotic photochemistry under a red dwarf's light do something unexpected? Or would we be forced, reluctantly and carefully, to say that the simplest explanation was that some form of life existed in those alien waters, exhaling sulfur-bearing molecules into the sky? Over the next year and a half, Webb turned its eye back to K2-18b more than once. Each transit was an opportunity to deepen the spectrum, to reduce the noise, to see whether the suspicious feature rose above the randomness of photon counting and instrumental whisper. Modeling teams refined their retrieval codes, adjusting how they treated clouds and hazes, exploring different assumptions about temperature profiles and atmospheric structure. The planet, in a sense, was being asked the same question repeatedly. What is in your air? In mid-April of the year 2025, the answer that came back was sharp enough to carry beyond the confines of specialist journals. A new analysis, drawing on additional Webb observations and using updated retrieval methods, reported that features consistent with dimethyl sulfide and a closely related molecule, dimethyl disulfide, were present in the spectrum at a level that, statistically, rose to what scientists call 3 sigma. In plain terms, this meant that, under the model assumptions used, the likelihood that the signal was just a random fluctuation masquerading as a real feature was estimated to be about 3 chances in 1,000, or, to flip the perspective, about 99.7% confidence that something genuinely spectral was there. It is important to be precise about what that number refers to. The 99.7% does not mean there is a 99.7% chance that life exists on K2-18b. It does not even mean there is a 99.7% chance that the gas in question is truly dimethyl sulfide and dimethyl disulfide, as opposed to some other combination of absorbers that produce a similar shape under different modeling choices. It is a statement about how likely it is that the observed feature is a real part of the data, given the noise properties assumed, rather than a random wiggle. From there, a whole chain of interpretations has to be built, each with its own uncertainties. That nuance did not always survive the leap into headlines. Around the world, articles appeared with phrases like, "strongest evidence yet" of life on an alien world. The number 99.7 began to float free of its statistical anchor and edged toward a more general impression of near certainty. For many readers, the story condensed into something like, Webb has found gases that on Earth are only made by life, at a confidence level just shy of absolute proof. The combination, emotionally, was explosive. Inside the scientific community, the mood was more mixed and more measured. On the one hand, seeing 2 sulfur-bearing molecules that, on Earth, are closely associated with marine microorganisms, in an atmosphere already showing the hallmarks of a Hycean candidate, was undeniably striking. It lined up with predictions that had been sketched years earlier, in which ocean-covered, hydrogen-rich worlds might host microbial biospheres that vent exactly such compounds into their skies. On the other hand, many researchers were quick to point out that 3 sigma, while suggestive, is not the gold standard for extraordinary claims. Particle physicists, for example, typically demand 5 sigma, or a much smaller probability of a false detection, before declaring a discovery. Even so, the sense that something momentous might be unfolding was hard to ignore. Imagine being a student of astrobiology and seeing, in real time, the first serious, data-anchored discussion of possible life on a world 100 and more light-years away. Imagine being an older scientist who had spent decades working on biosignature theory, watching the abstract examples in papers give way to actual spectra from a real planet. The hypothesis that microbial life could exist in a K2-18b ocean, once a speculative scene in a conference talk, acquired a new weight. It had numbers behind it. It had plots and error bars and cross-checked retrievals. In interviews and public lectures, some of the researchers involved tried to convey both the excitement and the caution. They described how, in a hydrogen-dominated atmosphere above an ocean, methane and carbon dioxide could be linked through cycles that involve outgassing from the deep, dissolution into water, reactions at the sea surface, and return to the air. They explained that, on Earth, life often acts as a catalyst in such cycles, speeding up reactions, favoring certain pathways, and thereby changing the relative amounts of gases in ways that would not occur in a sterile environment. They painted a picture of K218b not just as a passive world being warmed by its star, but as a potentially active, chemically restless system. Then they layered dimethyl sulfide and dimethyl disulfide onto that picture. If an ocean exists under those hydrogen-rich skies, they suggested, and if microbial life has evolved there that resembles Earth's plankton in at least one respect, then those organisms might produce sulfur compounds that escape into the air, accumulate to detectable levels, and tweak the formation of clouds. The presence of both carbon-bearing and sulfur-bearing molecules in a specific pattern might then be more naturally explained by biology than by chance. It was not a claim of proof, it was a claim that the balance of plausibilities had shifted. In the broader culture, the echoes were unmistakable. Commentary pieces compared the situation to the opening of the film Contact, where a pattern in radio noise turns out to be a structured signal, or to the slow realization in Arrival that the strange shapes on the screens are language. Here, there were no aliens sending blueprints, no hovering ships, only a faint, precise change in starlight. Yet for many, this was more powerful. It was not a story someone had invented. It was a pattern the universe itself had drawn, and we had finally built an instrument capable of seeing it. At the same time, there was a quieter, more personal response among people who had never spent a day thinking about retrieval algorithms. For some, the idea that a telescope, parked far from Earth, could sniff out traces of what might be the breath of alien plankton was almost overwhelming. It turned the concept of distant ocean from a metaphor into something that felt physically present. That world, K218b, which until recently had been a string of catalog numbers and orbital elements, became, for a moment, a place, a dim, cold star in Leo, a planet circling it, a perhaps real, perhaps imagined layer of water mist and cloud over a deep sea. It is easy, in such a moment, to drift into certainty, to slide from "this could be life" into "this is life." The human mind likes crisp endings, clear resolutions. It likes to stand somewhere solid. Yet, if there is a theme running through the entire story of exoplanets and astrobiology, it is that nature resists such neatness. Almost every time we have thought we understood a class of objects, new data have revealed unexpected diversity. Hot Jupiters, super-Earths, mini-Neptunes, tidally locked habitable zone planets around red dwarfs. Each has forced us to revise. The same is likely to be true for biosignatures. Dimethyl sulfide and dimethyl disulfide may turn out to be exactly what they appear, a chemical whisper from a far-off ocean, or they may be the products of non-biological processes we have not yet fully mapped, especially under conditions very different from those on Earth. The 3 sigma figure may hold up as more data are collected, or it may erode as additional observations reveal subtle systematic effects in the instruments or the star. Other teams, using different modeling frameworks, may arrive at different levels of confidence. What the April announcement did, more than anything, was to push the question of life on K218b out of the realm of private speculation and into the center ring of scientific discourse. The hypothesis of a microbial ocean biosphere there stopped being pure fan fiction and became a live, testable idea. It was framed in terms of molecules, confidence levels, and retrievals that could be challenged, supported, or refuted. That is how belief in science matures. Not by becoming rigid, but by accepting the discipline of evidence. And because science is built as much on doubt as on hope, the very next step after such a claim is not celebration but stress testing. The planetary community, which had just watched this possible signal rise from the noise, began almost immediately to ask how it could be wrong. Were there overlooked sources of sulfur chemistry in hydrogen-rich atmospheres? Had the models of clouds and hazes been too simplistic? Were there instrumental quirks in Webb's detectors, subtle drifts, or scattered light effects that could produce or exaggerate the features attributed to dimethyl sulfide? Upcoming observing time was scheduled not only to strengthen the signal, if it was real, but to poke at its weak points. That is where the story bends, in the chapters that follow, from crescendo toward confrontation. Having, for the first time, allowed ourselves to ask, with some seriousness, is there someone there? We then have to live with the answer that comes back when we interrogate the data with all the skepticism we can muster. Skepticism, when it finally arrives, does not care how beautiful a hypothesis is or how much hope is wrapped around it. It cares only whether the evidence can stand when everything that might break it is brought to bear. There is an old, quietly ruthless principle that runs through the heart of science. Extraordinary claims require extraordinary evidence. It is not a slogan meant to dampen curiosity. It is a kind of safety rail, installed after centuries of falling for things we wanted to be true. The suggestion that a planet more than 100 light-years away might host an ocean biosphere venting dimethyl sulfide into its sky falls very squarely into the category of extraordinary. The evidence, therefore, had to be pressed, pulled, and tested until either it snapped or it held. After the first wave of Webb analyses on K218b, the ones that highlighted methane, carbon dioxide, and that tentative whisper of dimethyl sulfide, other teams did exactly what a healthy community is supposed to do. They took the same raw data and fed it into different retrieval codes. They played with the assumptions about clouds and hazes, about the temperature gradient with altitude, about how to model the star's own spectrum. Some groups found patterns that supported a sulfur-bearing molecule, in addition to the more robust methane and carbon dioxide. Others found that, under slightly altered modeling choices, the need for dimethyl sulfide almost evaporated. To a non-specialist, this can sound suspicious, as if the result depends entirely on who is doing the analysis. In reality, it reflects how delicate the situation is. The signal we are trying to read is small, layered on top of other signals, like a faint melody playing against a background of static, room noise, and overlapping instruments. If you assume a different shape for the background, you may hear the melody more clearly or not at all. That is why multiple independent attempts are so valuable. They map out which features are robust in the spectrum and which are more sensitive to method. In this case, the methane and carbon dioxide proved stubborn. Across different teams and different retrieval frameworks, those molecules kept reappearing as the best explanation for certain broad, deep dips in the infrared spectrum. The overall picture of a hydrogen-rich, water-influenced atmosphere in the habitable zone remained. What shifted was the status of the small, sharp features that had been tentatively linked to dimethyl sulfide and its cousin dimethyl disulfide. For some analysts, they stayed at the level of an intriguing bump. For others, they sank back toward the noise. As more eyes turned to the problem, it became clear that one of the key questions was not simply, is there a feature here? But, how well do we understand the way Webb itself behaves at these wavelengths and flux levels? Tiny drifts in instrument temperature, scattered light inside the optics, subtle quirks in the detectors, all can imprint patterns that, if not modeled correctly, might masquerade as or erase real atmospheric signatures. The Webb teams had done years of ground testing and early in-flight calibration. Still, no instrument is perfect, and no calibration is ever final. As the first exoplanet spectra accumulated, so did the list of instrumental subtleties. By the middle of the year 2025, the question of dimethyl sulfide on K218b had become pressing enough that a larger, coordinated effort was organized. Under the umbrella of a NASA-led collaboration, scientists from multiple institutions and with experience in different aspects of the telescope and the data pipelines came together to perform a fresh reanalysis. Their goal was not to confirm or deny any one group's earlier result, but to take a step back and re-examine everything from the ground up. The raw photon counts, the correction for detector effects, the models of the star, the treatment of time-dependent noise, and finally the retrieval of atmospheric composition. In July of that year, their conclusions were made public. The language was restrained, but the message was clear. When they applied their best understanding of Webb's systematics and used a suite of retrieval methods, the evidence for methane and carbon dioxide in a hydrogen-dominated atmosphere remained strong. The absence of ammonia, relative to what a simple equilibrium chemistry model would predict, also held. These features, taken together, continued to support a picture in which K2-18b is a water-rich, potentially Hycean candidate, a planet in the habitable zone with a thick envelope of light gases and complex chemistry. The case for dimethyl sulfide, however, did not survive at the same level. In the NASA-led reanalysis, the spectral regions that had been identified as possible signatures of sulfur-bearing organics were found to be compatible with noise once updated corrections and broader model comparisons were applied. In some runs, the retrieval codes did favor small amounts of such molecules, but the statistical significance fell below thresholds that the team was willing to treat as compelling. Their summary was, in essence, that if dimethyl sulfide exists in the atmosphere of K2-18b, its imprint sits below the level where Webb, at least with the current data and methods, can robustly separate it from the background. For people who had been holding on to the 99.7% figure in their minds as evidence of life, this felt, understandably, like cold water poured over a fire. Headlines that had skirted the edge of declaration now had to step back. The earlier 3 sigma confidence referred to one kind of analysis under a particular set of assumptions. Under a wider, more conservative lens, that confidence shrank. The extraordinary claim about a sulfur-based biosignature, for the moment, lost its footing. If you zoom out, though, this sequence is not an embarrassment. It is a textbook example of how science protects itself from its own optimism. A team makes a bold but carefully framed claim based on the best tools they have. Others test that claim using different tools. A larger collaboration, with access to deep knowledge of the instrument and a mandate to be conservative, weighs in. What cannot survive that process in a robust way is set aside, not necessarily as wrong, but as not yet proven. What remains is a core of results that everyone can stand on. In this case, the detection of key carbon-bearing molecules in a habitable zone atmosphere. We have been here before, in different forms. On Earth, a famous cautionary example landed, quite literally, from space. In the early 1980s, a meteorite was found in the Allen Hills region of Antarctica. Because of its composition and trapped gases, it was eventually identified as a fragment that had been blasted off Mars long ago and drifted through space before falling onto the ice. It was catalogued as ALH84001. For years it sat in collections, studied for what it could say about Martian geology. Then, in the mid-1990s, a team examining the meteorite under powerful microscopes and with various chemical probes found structures and mineral arrangements that they argued could be fossil traces of ancient Martian microbes. In August of 1996, NASA held a press conference. The idea that we might be holding a piece of another world that contained tiny, fossilized organisms triggered a wave of excitement. The United States president at the time made a speech. Newspapers ran front-page stories. For a moment, the narrative that life had once existed on Mars and that we had evidence in hand seemed to step out of science fiction. In the decades that followed, that initial interpretation was subjected to intense scrutiny. Other researchers showed that the same kinds of structures and minerals could be produced by non-biological processes: heating, shock from impacts, chemical alterations in rock that had nothing to do with cells. The field did not converge on a consensus that this is life. Instead, it gradually leaned toward this is not convincingly life. Today, while there are still a few voices defending the original claim, the majority view treats the ALH84001 microfossil story as unconfirmed at best, and likely a case where desire outran the strength of the evidence. The lesson is not that we should never entertain bold interpretations. Without boldness, many of the most interesting ideas in astrobiology would never be articulated. The lesson is that the more transformative a claim would be if true, the more aggressively its foundations must be tested. Dimethyl sulfide on K218b sits in that same category. It is precisely because such a detection would be so profound, hinting at living oceans under alien skies, that the bar for accepting it as real is so high. There is also a more specific, technical reason to be cautious when sulfur-bearing organics are involved. In a hydrogen-rich atmosphere exposed to high-energy radiation from a star and bombarded by charged particles, photochemistry can be extremely productive. Ultraviolet photons can break apart simple molecules, allowing their fragments to recombine into a variety of larger species. Sulfur, in particular, is a versatile player, starting from basic reservoirs like hydrogen sulfide or sulfur dioxide. Networks of reactions can build chains that resemble, in some respects, the structures of dimethyl sulfide and related compounds. On Earth, these pathways exist, but are overshadowed by the biosphere's far more efficient and directed production. In an exoplanet atmosphere very different from our own, with higher hydrogen content, different temperatures, and a red dwarf spectral energy distribution, non-biological routes to complex sulfur organics may be more prominent. Our libraries of laboratory cross-sections and reaction rates for these conditions are incomplete. That means we can easily underestimate how much abiotic chemistry can mimic what we, from our home-biased perspective, have labeled as signatures of life. End quote. Communicating this to a general audience is tricky. It is tempting to say, on Earth, dimethyl sulfide is made by life. Therefore, elsewhere, seeing it means life. The missing step is the question, have we exhausted all conceivable non-biological ways of making similar spectra in that environment? In a field where we have only one known biosphere and no direct access to exoplanet atmospheres beyond their light, the honest answer is usually no, not yet. It's so, layered on top of these chemical uncertainties are the raw difficulties of the observing method. Transit signals for small, temperate planets are minuscule. The fraction of starlight that filters through the atmosphere, rather than passing by or being blocked by the planet's bulk, is tiny. The resulting spectral features are changes of a few parts in 10,000 in the overall flux, sometimes less. Over the many hours of a transit, Webb's pointing must remain extremely stable, its detectors must be monitored for drifts, and the pipeline must subtract instrumental patterns that can be comparable in size to the atmospheric signatures we seek. Furthermore, the star itself is not a perfectly steady light bulb. Red dwarfs can exhibit spots, flares, and subtle variations that change the spectrum over time. If a dark spot rotates into view during a transit, the apparent depth of certain spectral lines may shift in ways that could be misconstrued as planetary features if the stellar behavior is not properly modeled. Clouds and hazes on the planet can mute or reshape absorption features, making some molecules harder to see and others easier to misinterpret. All of these factors mean that turning a transit spectrum into a list of atmospheric constituents is as much an exercise in understanding what else can produce a given pattern as it is in matching that pattern to a molecule. This is why the cycle of claim, critique, and refinement is not a sign of chaos, but the mechanism by which truth is approached. A promising signal is identified. Its implications are sketched out. Then, an army of skeptics, many of them motivated precisely by the hope that the signal might be real, try to break it. They test for instrumental artifacts. They invent alternative chemical pathways. They alter assumptions about clouds and stellar activity. If the signal survives that onslaught, it gains credibility. If it does not, the community steps back, incorporates the new understanding into its models, and moves on. In either case, knowledge increases. Popular stories have latched onto this pattern in their own way. In many thrillers and science fiction films, there is a scene where a supposed sign of life turns out to be a glitch, a hoax, or a misunderstanding, building tension before the real contact arrives. A false alarm on Mars, a misread satellite feed, a pattern in noise that looked like a message but was not. In those narratives, the twist serves drama. In real life, the process is less cinematic but more important. Peer review, replication, and reanalysis are the tools that prevent our desire for company in the universe from turning every ambiguous hint into a premature conclusion. If you return, after all this, to K218b, the picture may feel a little cooler, a little more sober, but it is far from empty. Even without a confirmed detection of dimethyl sulfide, the planet remains extraordinary in what it has already taught us. We have a world in the habitable zone of another star, intermediate in size between Earth and Neptune, for which we have direct evidence of a hydrogen-rich atmosphere containing methane and carbon dioxide with indications of water. That alone is a milestone. It is one of the first times we have characterized, in any detail, the air of a planet that sits at the right distance from its star for liquid water to be plausible. More than that, K218b has served as the first full dress rehearsal for a biosignature investigation beyond the solar system. The community has walked through every step that, in some future case, might lead to a genuine declaration of life. Initial detection of interesting molecules, theoretical work on possible biological and non-biological sources, careful evaluation of instrument systematics, independent reanalyses, and a high-profile, agency-level reassessment. The fact that, in this instance, the most dramatic candidate biosignature gas likely falls short of firm detection does not render the exercise a failure. It shows that the machinery of skepticism functions. In a way, K218b has become a kind of training planet, a test of our ability to keep our heads while looking at data that resonates deeply with our hopes. It sits there, a dim point in the constellation of Leo, continuing its steady 30-something day circuits around its small red star, indifferent to the debates playing out in conference halls and journals on a distant Earth. Whether or not life stirs beneath its clouds, the light it has sent us has already forced us to confront how we will respond when, someday, a spectrum arrives that may be even harder to explain away. If K218b has taught us anything, it is that resting our hopes on a single world is a fragile way to face a galaxy. If the universe is generous with life, we should expect its traces to be scattered across many skies, not entrusted to one lonely ocean under hydrogen clouds. Over the past few decades, as telescopes like Kepler and TESS have scanned the sky, a quiet portfolio has been building. Instead of one suspect world, we now have a list, each with its own quirks and caveats, each a different way the universe might choose to host biology. Some of them are harshly lit by red dwarfs, some sit under calmer suns. Together, they make it harder to believe that K218b, whatever its verdict, is the only place worth watching. One of the most arresting entries in that list orbits a small, cool star in the direction of Aquarius. The star is called TRAPPIST-1, and on February 22nd in the year 2017, a group of astronomers announced that 7 planets, all roughly similar to Earth in size, were circling it. The numbers alone were startling. Until then, we had seen systems with 1, 2, perhaps a few known planets. Here was a miniature planetary family packed into a space smaller than the orbit of Mercury, with at least 3 of those planets sitting in the star's habitable zone. TRAPPIST-1 itself is a faint red dwarf, much smaller and cooler than the Sunday. Its planets huddle close, with orbits measured in only a handful of days. That intimacy means that, from the star's perspective, transits are common. From ours, each transit is a gift. Every time one of those 7 worlds passes across the face of TRAPPIST-1, it offers a chance, present or future, to look for an atmosphere. The system instantly became a laboratory for comparative habitability. Instead of arguing forever about one planet's conditions, scientists could imagine testing several in the same environment, each receiving different amounts of starlight, each perhaps displaying a different climatic outcome. Not all the news about such red dwarf systems is comforting. Stars like TRAPPIST-1 are often active, throwing flares and high-energy particles into space. Planets this close are likely tidally locked, showing the same face to their star the way the Moon shows one face to Earth. Some models suggest that atmospheres under such conditions might be stripped away, or that the contrast between blazing daylight and frozen night would be extreme. Other simulations, however, paint a more forgiving picture. Thick atmospheres and oceans can redistribute heat, smoothing the temperature differences. a permanent band of twilight, neither scorching nor frozen, can emerge along the line between day and night, providing a stable refuge where liquid water and tolerable climates could persist. The truth is probably nuanced. Some red dwarf planets may indeed be stripped and sterile. Others may manage to hold onto their air and seas for billions of years. TRAPPIST-1 gives us multiple rolls of that particular cosmic dye, close enough that Webb and future observatories can study them in detail. It is no wonder that, when people imagine future headlines about atmospheric biosignatures, the names of those 7 planets often hover in the background, waiting. A little farther out in space, circling a different small star, another world has joined the roster. On January 3rd, in the year 2020, astronomers confirmed a planet designated TOI 700d. The initials stand for TESS Object of Interest, a reminder that this system came to light through the survey work of the transiting satellite. TOI 700d is close in size to Earth and orbits within the habitable zone of its host star, receiving roughly a little less energy from its sun than Earth does from ours. Climate models, when given a range of plausible atmospheres, find many scenarios in which liquid water could exist on its surface. Like TRAPPIST-1, the TOI 700 system is not a sun clone. Its star is cooler and smaller. Tidal locking, stellar activity, and the history of the star's brightness all influence whether TOI 700d is a clement world or a desiccated rock. We do not yet know whether it has an atmosphere, let alone what that atmosphere contains. But in the growing pattern of data, it serves as another point, an Earth-sized planet in the right energy band around a relatively nearby star, ready to be probed as instruments improve. Closer still, in our own neighborhood, a very dim, very cool star called Teegarden's star has its own pair of candidates. Announced in the year 2019, Teegarden's star B and Teegarden's star C are inferred from the tiny gravitational tug they exert on their host. The star itself lies only about a dozen light-years away, practically down the street on a galactic scale. Both planets appear to sit near or within the star's habitable zone, although, as always, the details hinge on their atmospheres, their rotation states, and their histories. What makes the Teegarden pair compelling is their proximity. Worlds at such short distances are prime targets for future generations of telescopes that might, one day, be able to directly image planets as faint dots next to their stars, or to resolve their light well enough that spectra become easier to interpret. If you imagine a time when we can routinely map weather patterns on exoplanets or measure seasonal changes in their gases, it is systems like Teegarden's that will likely be among the first to submit to that level of scrutiny. Underneath these individual stories, there is the quiet, statistical drumbeat of Kepler's legacy. By watching one patch of sky for years and cataloguing transits, Kepler did more than announce particular planets. It told us about frequencies, from the fraction of stars that showed Earth-sized planets in or near the habitable zone, and from corrections for the geometric chances of those planets crossing from our line of sight. Astronomers have estimated that such worlds may be common, not rare jewels, but a standard outcome of planetary formation. Depending on the exact criteria used, the numbers suggest that there could be tens of billions of potentially habitable, roughly Earth-sized planets in the Milky Way alone. That phrase, tens of billions, is easy to gloss over. We are used to big numbers in astronomy, but if you translate it into a picture, it gains weight. Imagine placing the Sun at the center of a three-dimensional map and then plotting every star around it within a certain radius. Now, among those stars, mark each one that likely has a planet roughly the size of Earth in its habitable zone with a small, glowing dot. The resulting pattern is not a sparse scattering of points. It is a thick, fuzzy cloud, densest near the Sun and thinning gently outward, each glow representing a world where temperatures and sizes might permit liquid water under some range of conditions. We do not know how many of those dots truly host oceans, climates, and atmospheres. We do not know how many harbor life. What the map tells us is that the raw real estate is there. When we single out K2-18b, TRAPPIST-1's planets, TOI 700d, Teegarden's star B and C, We are not plucking miracles out of a desert. We are selecting examples from an enormous underlying population. If the cosmos has been generous with biology, it has had plenty of surfaces to work with. Of course, each of these suspect worlds carries its own set of complications. Red dwarfs, so abundant in the galaxy and so appealing for transit spectroscopy because of their small sizes, may also be harsh landlords. Their flares can bathe planets in ultraviolet radiation. Their early evolution can involve long, bright phases that bake close in worlds when they are young. Planets tightly bound to such stars may end up with one side constantly illuminated and the other forever in darkness, a state that challenges our Earth-based intuitions about climate. Here again, models bring nuance. Tidally locked planets with thick atmospheres can, in simulations, maintain surprisingly stable climates, with jet streams and circulation patterns that move heat from day to night. The line of perpetual sunrise and sunset, the Terminator region, can be temperate even if the substellar point is hot and the far side is cold. Oceans, if present, can transport heat as well. Magnetic fields, depending on rotation and internal dynamics, may shield atmospheres from stellar winds, though this remains an area of active work. The result is a set of arguments that do not dismiss red dwarf planets as hopeless, but treat them as challenging and diverse. As the science has matured, so has the way we weave these worlds into our stories. Modern fiction has started to borrow real exoplanets for its settings. Authors name-check TRAPPIST-1, Proxima Centauri b, or Kepler-discovered worlds, grounding their narratives in places that genuinely exist, with real stellar types and distances. Films and series incorporate the idea that a planet around a dim red star, locked in tidal embrace, might host life in a twilight belt. The public imagination, once populated mainly by vague other Earths and vague alien planets, is slowly being trained to associate the word exoplanet with specific, catalogued, physically characterized places. This cultural shift matters because it prepares us, quietly, for the kind of evidence Webb and its successors will bring. When a spectrum from a planet with a name like TOY 700d or Teegarden star C shows a certain pattern of gases, it will not be just math on a page. It will be a reading from a world we have already pictured, however roughly. The line between data and story will not vanish, but it will thin. If K218b, under the weight of new analyses, eventually sheds its status as a strong biosignature candidate and settles into the role of a fascinating but lifeless Hycean or mini-Neptune, it will be a disappointment for those who hoped this might be the first confirmed alien ocean biosphere. Yet, the broader deck of suspect worlds remains on the table. TRAPPIST-1's 7 planets still march through their orbits, offering transits to any patient watcher. TOI 700d still circles its star in a zone where water could flow. Teegarden's 2 candidates still glimmer in our near backyard. Behind them, the Kepler-derived cloud of potential habitable worlds still hangs over the galactic map. A single card might turn out to be weaker than it first appeared. The hand, however, is strong. The hypothesis we set at the beginning that the universe favors life, not exceptions, does not stand or fall on dimethyl sulfide in one atmosphere. It leans on the sheer abundance of possible homes, on the chemistry that seems to flourish wherever water, rock, and energy meet, and on the growing list of planets that sit, quietly and persistently, in the right kind of light. If the sky around us is crowded with possible homes, then the question of whether the universe favors life does not start light years away. It starts here, in the small family of worlds we already share a star with. For most of human history, the solar system was imagined as a set of sharp categories. Earth was alive. Everything else was rock and gas and ice. Mars was a red desert. The outer moons were cold marbles. Comets were streaks of frozen dust. The idea that our own planetary system might hold several plausible niches for life at once would have sounded extravagant. Yet as probes and rovers and orbiters have done their long, patient work, that old picture has thinned. What we see now is a system where rock, water, and energy have come together in multiple places, each a different experiment, each a small argument against the notion that biology is a fragile, one-time accident. Mars is the most obvious of these laboratories. From Earth, through telescopes, it looks dry and still, its thin atmosphere barely clinging to the surface. But once we started sending spacecraft to orbit and land, the story changed. High-resolution images revealed ancient river valleys carved into the crust, delta fans where water once slowed and dropped its sediment, layered rocks laid down in what were clearly once lakes. Rovers rolling across the dusty plains have scraped at stones and found clays and sulfate minerals that only form in the presence of liquid water. Some of those deposits, by their chemistry and texture, look very much like the habitable sediments that on Earth would be prime real estate for microbial mats. In the laboratories carried within their metal bodies, missions like Curiosity and Perseverance have heated drilled samples and sniffed the gases that emerge. They have detected organic molecules, the carbon-bearing fragments that, while not themselves proof of biology, show that the raw materials for life existed in Martian rocks long ago. Orbiters, scanning from above, have mapped out patches where transient methane seems to appear and vanish with the seasons or with geography, though the measurements are difficult and sometimes contradictory. A few recent claims about unusual chemical patterns in the air and in ancient rocks have sparked debate over whether we might be seeing the edge of a biosignature, or only complex inorganic chemistry in an environment that no longer looks completely sterile. So far, no one has held up a Martian cell under a microscope and said, "This is alive." No image from Mars has shown motile organisms, no drill has pulled up undisputed microfossils. What we have instead is a close approach, a world that clearly had surface water, energy sources, and organic chemistry for long stretches of its early history, and that may still have subsurface aquifers or brines. If life does not exist there now, it is not because conditions were impossibly hostile for all of time, but because other factors, perhaps loss of atmosphere or changing climate, intervened. Mars stands as a reminder that habitable environments can arise and disappear, and that a single planetary system can host both living and dead experiments. Farther out, beyond the asteroid belt, orbiting the giant planet Jupiter, a different kind of habitat hides behind ice. Europa is a smooth, bright moon, its surface crisscrossed by dark lines and broken plates. For a long time, the leading interpretation of that cracked shell has been that it floats atop a global subsurface ocean. Gravity measurements, magnetic field interactions, and theoretical modeling all point toward a deep layer of liquid water beneath the ice, kept from freezing by tidal flexing, as Europa moves through Jupiter's gravity well. In that ocean, shielded from radiation, there could be warm spots where the rocky mantle meets the water, places where chemical gradients might resemble the hydrothermal vents on Earth's seafloor. Hints that this ocean might communicate with space have added to the intrigue. Observations with the Hubble Space Telescope and other instruments have suggested that, at least occasionally, plumes of water vapor erupt from Europa's surface, spraying material into space. If those plumes are real and can be sampled by a passing spacecraft, they offer a rare gift. A way to taste the chemistry of a buried sea without drilling through tens of kilometers of ice. In that scenario, Europa becomes the prototype for a dark ocean life world, where sunlight never reaches the water. But chemical energy from the interior might power microbes. Saturn's small moon Enceladus tells a related, and in some ways even starker, story. When the Cassini spacecraft arrived in the Saturn system and began to explore its moons, Enceladus looked at first like a minor character, a bright, icy sphere. But Cassini's instruments detected something unexpected. Narrow jets of material spraying from fractures near the moon's south pole. Tiny geysers feeding a faint ring of ice particles around Saturn. When Cassini flew directly through those plumes and sampled them, the results were startling. The particles and vapor contained water, salts, and a variety of organic molecules, ratios of certain compounds, and the presence of molecular hydrogen. suggested that hot water was interacting with rock at the bottom of a subsurface ocean, driving hydrothermal activity. In other words, Enceladus appears to have, beneath its ice, a warm, salty ocean in contact with a rocky core, venting material that contains both the ingredients and the energy sources that, on Earth, support rich microbial ecosystems around deep-sea vents. Here, in a tiny moon whose entire diameter is smaller than many countries on Earth, we have a plausible setting for life. Rock, plus water, plus energy, cycling, and mixing over long timescales, with organics delivered and processed. If a mission someday returns there, built specifically to fly through those plumes with life detection instruments tuned to the smallest clues, it will be one of the most focused tests of the dark ocean hypothesis we can perform without leaving our own system. When you connect these cases back to the earlier story of meteorites and comets, the pattern sharpens. The Murchison meteorite showed that interplanetary space is capable of assembling complex organic molecules and delivering them intact to planetary surfaces. Comets, when heated near the Sun, release gases and dust that include a rich mix of carbon-based compounds, as we have seen with missions that have flown by or even touched their surfaces. If organics are made in the cold between worlds and then scattered widely, and if multiple bodies in a system have liquid water layers and internal energy sources, then the simple recipe, rock plus water plus energy, leads to potential life, ceases to be speculative rhetoric. It becomes a direct extrapolation. The same ingredients keep showing up, in different combinations, in multiple places. The honest status, right now, is that we have no direct, unambiguous detection of life anywhere beyond Earth. No microscopic organism from Mars in a sealed dish, no measured metabolism from European ocean samples, no genetic sequences from Enceladus plume particles. But the picture of the solar system as a collection of utterly sterile rocks and gases has been pushed far back. Where once it was plausible to imagine only one habitable environment per system, we now look at our own star's retinue and see, at minimum, a handful of serious contenders. Past surface lakes and present subsurface ice on Mars, buried oceans on Europa and Enceladus, perhaps deep liquid layers on other moons like Ganymede or Titan, and transient warm niches in places we have not yet probed. This shift has echoed into our stories. From the film often known as 2001, A Space Odyssey, with its enigmatic monoliths buried on the moon, to series like The Expanse, which hinges much of its drama on the discovery and weaponization of an alien protomolecule within our own planetary backyard, there is a recurring pattern. The turning point does not happen in the distant reaches of another galaxy. It happens in a crater on Mars, in the oceans under the ice of Europa, in the rings of Saturn. The leap from a sterile solar system to one that harbors microbial life feels, intuitively, smaller than the leap from microbes to radio beacons and star-spanning civilizations. As a result, fiction often stages its first contact events at home, in the places our robots can reach. That instinct is not entirely detached from reality. If life emerges readily when conditions are favorable, then a planetary system that manages to produce one biosphere may well produce more. A planet and a moon, a pair of moons, a past surface biosphere and a present subsurface one, all orbiting the same star. Our own system, with its tantalizing hints and partial evidence, may be a typical example. If that is the case, then when we look outward at systems like K218 or TRAPPIST-1, we should not think in terms of a single lucky planet per star, but in terms of clusters of potential. One world in the habitable zone, another with a buried ocean, perhaps a third with transient lakes or deep, high-pressure seas. Seen from that perspective, the atmospheric hints we are starting to extract from exoplanets are not isolated teasers. They are the first glimmers from a universe where habitable pockets might be common within each system. The fact that Mars, Europa, and Enceladus all present plausible niches, even after decades of study, makes it much easier to imagine that K218b could have a deep ocean, that one or more TRAPPIST-1 planets might sustain a twilight habitable belt, that some yet unnamed moon around a distant giant planet might hide water under ice. If life could be hiding, undetected, in brines beneath Martian dust, in dark seas under European ice, or in the vent-fed depths of Enceladus, then the idea that distant systems host only lifeless rocks begins to look timid. Our own backyard whispers that biology does not need much, just the right combination of rock, water, energy, and time. Everything else, all the complexity that follows, is an elaboration on that theme. If the ingredients of life arrange themselves so easily in rocks and oceans and ice, there is a question that hangs in the air like a held breath. If the universe is busy with biology, why does the sky feel so quiet? There is a story, often told and retold, that begins in a laboratory lunchroom in the middle of the last century. In the summer of 1950, the physicist Enrico Fermi was eating with colleagues, talking about flying saucers and newspaper stories and the possibility of beings elsewhere. The conversation drifted toward the age and size of the galaxy, the vast number of stars, the time it would take for a spacefaring civilization to cross from one side to the other if it chose to spread. At some point, Fermi put his sandwich down and asked a simple question that cut through all the speculation. Where is everybody? On its face, the question is almost childlike. Underneath, it is sharp. The universe is old. The Milky Way alone holds hundreds of billions of stars. If even a small fraction of them host planets, and if even a small fraction of those planets develop life, and if even a small fraction of those living worlds produce technological civilizations that choose to explore or communicate, then it seems as if someone should have left a mark we can see. A beacon, a probe, a megastructure dimming a star, a flood of radio chatter. Instead, as far as our instruments and our eyes can tell, the sky is indifferent. This tension between expectation and observation is what people now call the Fermi paradox. There are many ways to soften that paradox, and none of them require abandoning the idea that the universe could be rich in life. The first is to note that life and intelligence are not the same thing. Microbes do not build radio dishes. Forests and coral reefs can reshuffle atmospheres and chemical cycles without ever developing languages or mathematics. It may be that biology arises fairly often where there is rock, water, and energy, but that the specific evolutionary pathways that lead to creatures capable of technology are rare. The chain from single cells to toolmakers crosses many thresholds. On Earth, it took billions of years. A second possibility is that intelligence may be common, but the phase in which that intelligence produces signals we can detect is brief. A civilization might discover radio, use it promiscuously for a few centuries, then move on to communication systems that are harder for outside observers to notice, or collapse, or choose deliberately not to broadcast. If the window during which a society fills space with easily detectable noise is short, then the odds that two such windows overlap in time and that our instruments are pointed in the right direction during that overlap become small. The galaxy could be full of civilizations, each lighting up for a moment on cosmic timescales and then going dark, without any two ever hearing each other. A third angle focuses on the technologies themselves. Much of our searching so far has been tuned to the kinds of signals we ourselves know how to make. Narrowband radio transmissions, bright, coherent flashes of light, large, rigid structures orbiting stars. But an older or different kind of technical species might use channels we have not thought to monitor, or that blend into natural background in ways we have not learned to disentangle. In that view, the silence we hear is partly a reflection of our own narrowness. Threaded through all of these ideas is a more sobering concept known as the Great Filter. Imagine the development of an advanced, long-lived civilization as a series of steps. Planets form, life emerges, life becomes complex, intelligence appears, technology is mastered. Tools are used in ways that do not destroy the environment that supports their makers. Each transition has some difficulty, if at least one of those steps is extremely hard, in the sense that only a tiny fraction of worlds ever manage to pass it, then that step acts as a filter. It allows only a few lines of evolution to continue. The unsettling part is that we do not yet know where, in that chain, the hardest steps lie. It could be that the great filter is behind us, that the jump from non-living chemistry to self-replicating cells is so unlikely that Earth is genuinely unusual in having made it. If that is true, then the universe might be dotted with sterile planets, and planets where chemistry never quite caught fire, and we are already beyond the main barrier. Or it could be that the filters lie ahead, that technology and self-restraint rarely coexist for long, that most civilizations wreck their environments or turn inward or otherwise vanish before they spread. In that case, the silence we hear is the sound of many failed attempts. For more than half a century, people have tried to turn Fermi's lunchtime question into an experimental program. Since the 1960s, projects grouped under the name SETI, the Search for Extraterrestrial Intelligence, have pointed radio telescopes at stars, looking for signals that would stand out from natural emissions. They have scanned narrow frequency bands, listened at wavelengths thought to be attractive for interstellar communication, and, more recently, applied algorithms to look for artificial patterns in wide swaths of data. So far, the result has been largely quiet. A few intriguing events have appeared and gone, with none repeating in the way a deliberate transmission almost certainly would. This silence is telling us something, but not necessarily what a first glance might suggest. It does not rule out microbial life on a million worlds. Radio searches are sensitive to loud, persistent broadcasters, to civilizations that choose to emit detectable signals over long periods. They cannot see silent oceans, buried biospheres, or species that never invent or employ radio in the way we have. The absence of whistles in the dark says little about the presence or absence of chemistry in alien seas. It mainly constrains the number of societies similar to our own that are shouting on purpose or by accident in the narrow bands we are monitoring. If you bring K218b back into the frame, the distinction sharpens. Even in the most optimistic reading of its spectra, no one is suggesting that there are cities under those hydrogen clouds, or that radio waves are spilling from that world across interstellar space. The picture on the table is of a planet with a deep ocean and a population of microorganisms that might, if we are lucky, be exhaling certain gases into the sky. Such a biosphere would be profoundly important. It would prove that life has happened at least twice, independently, in the universe we can observe. It would revolutionize biology and philosophy, but it would not make a dent in the Fermi paradox, as it is usually phrased. Because microbes do not light beacons. They do not build Dyson spheres. They do not produce the kind of techno-signatures we have been listening for. In that sense, the paradox may be partly a matter of framing. It is less, if life is common, why is the universe silent? And more, if communicative civilizations are common, why does the universe appear silent in the channels we are monitoring? Life silence and radio silence are not the same thing. A universe filled with K218b, like biospheres, could be roaring with metabolic activity at the microscopic scale and still present as hushed when you listen for narrow-band transmissions. Our stories have tended to focus on the loud possibilities. In films like Arrival, the drama hinges on deciphering richly structured signals from a clearly intelligent presence. Giant vessels hang over cities, symbols bloom on screens. The puzzle is about language and intention. These narratives resonate because they revolve around beings who are, at least in outline, like us, conscious, communicative, capable of narrative. In reality, if the universe is generous with life, it may be far more generous with the quiet forms than with the noisy ones. Microbial mats, planktonic swarms, forests without cities, reef worlds with no radios. Their presence would be written in atmospheric composition, surface chemistry, and faint seasonal changes, not in messages. That shift in emphasis is part of why observatories like Webb matter so much. If we accept that the Fermi question is mostly about the absence of clear technosignatures, then the most promising way to probe whether life, in the broader biological sense, is common, is not to wait for a message, but to look at planets and moons as ecological systems. Atmospheric chemistry, thermal balance, clouds, oceans, geological cycles. These become the channels where life, if it is present, might leave marks. Webb's ability to turn transits into spectra, to read the gases in a planet's sky, is a step toward listening for that quieter kind of presence. It is entirely possible to imagine a galaxy where, in system after system, planets like K2-18b circle dim stars, their deep oceans thick with microbial life, their atmospheres subtly shaped by metabolism, while no civilization ever rises to send radio waves across the void. It is also possible to imagine a galaxy where technological societies do arise, but so rarely and live so briefly in their broadcasting phase that by the time anyone is listening, most are gone. In both cases, the Milky Way would be profoundly alive and still fail to answer when we call in the way Fermi's colleagues might have expected. Seen in that light, the apparent silence we have encountered so far becomes less of a contradiction and more of an invitation to change how we ask the question. Instead of, "Where is everybody?" we might quietly shift to, "What is happening in all those distant oceans, under all those clouds?" The first question listens for voices like ours and mistakes the lack of an answer for emptiness. The second looks for chemistry, for disequilibria, for the subtle fingerprints of metabolism, and is prepared for the possibility that the universe, if it is full of life, may never introduce us to anyone, only to the patterns that life leaves behind. If the universe has been quietly asking us what we are willing to believe, then K2-18b is the place where we have chosen, for a moment, to answer under oath. Imagine a courtroom, not in a city, but in the space between stars. At the center is a single exhibit, a set of spectra, lines of data that represent how starlight has passed through the atmosphere of K2-18b. On one side of the room sits the pro-life argument. Not in the sense of politics, but in the literal sense of arguing that life may exist. On the other side sits skepticism, patient and unsmiling. The judge is not a person. It is the standard of evidence we have agreed to live by. The pro-life case opens with a broad gesture. On Earth, once conditions allowed, life seems to have appeared relatively quickly. In the geological record, the gap between a world of sterile rock and a world where simple cells left traces in ancient sediments is not enormous. As soon as there were stable oceans, energy sources, and a reasonably calm bombardment environment, metabolism seized the opportunity. That does not prove that life is easy everywhere, but it suggests that, given the right circumstances, chemistry is eager to step over that threshold. Next, the advocates point to the reach of prebiotic organics. They remind the court of the Murchison meteorite and of comet samples and of laboratory experiments. Complex carbon-based molecules, including amino acids and other building blocks, form in the cold between stars, on dust grains, in planetary disks, and in early atmospheres. They are delivered by rocks and ice. Planets and moons do not have to start from scratch. They are seeded by the universe's own slow chemistry. They call the solar system itself as a witness. Mars, with its ancient rivers and habitable sediments. Europa, with its hidden ocean. Enceladus, with its vent-fed plumes. Perhaps other moons like Ganymede or Titan as well. These are not rumors, but measured realities. We do not yet know whether life has taken hold in any of these places, but they are plausible habitats. Our own system, smallest of samples, already offers multiple niches where biology might exist or might have existed. If one star can host several such pockets, why should others not do the same? The advocates then widen the frame to the galaxy. Thousands of planets in or near habitable zones have been identified. Some are roughly Earth-sized. Some orbit small stars, some larger ones. A non-trivial number lie within distances where their atmospheres might be probed. Kepler's statistics tell us that habitable zone Earth-sized planets may be counted in the tens of billions in the Milky Way. TESS and other surveys have begun to name nearby examples we can actually point to. The universe, they argue, has not been stingy with potential homes. Only after laying this background do they circle back to K2-18b itself. Webb's spectra show a hydrogen-rich, water-influenced atmosphere. Methane and carbon dioxide are clearly present. with ammonia notably depleted relative to naive expectations. The planet sits in the habitable zone of its star. Its size and mass allow, though do not require, a deep ocean beneath its skies. In this context, the earlier claim of dimethyl sulfide and dimethyl disulfide at about 3 sigma, roughly 99.7% confidence as a real feature in the data, is presented as a tantalizing piece of circumstantial evidence, even if later analyses have weakened it. Taken together, the pro-life side argues, these factors make the hypothesis of a microbial ocean biosphere on K218b no longer a fantasy, but a serious, testable possibility. They rest their case not on certainty, but on plausibility. Chemistry seems eager to become biology when conditions allow. Those conditions are not unique. Prebiotic material is delivered widely. Our own backyard shows multiple plausible habitats. The galaxy is rich in habitable zone planets. Webb has, for the first time, shown us a habitable zone world, with a water-rich, methane and carbon dioxide-bearing atmosphere. Given this, they say, surely the burden of proof has shifted away from the idea that life is a singular accident. The skeptical side stands and walks to the same exhibit. They begin not by denying the data, but by narrowing the claim. It is one thing, they say, to show that a planet's atmosphere fits a certain model. It is another to assert that life is the best explanation for that model. Biosignatures, they remind the court, can be mimicked by non-biological processes, especially in hydrogen-dominated atmospheres under high-energy stellar radiation. Photochemistry can generate complex sulfur organics without any cells to guide it. Geological and atmospheric cycles can maintain disequilibria that resemble those life creates here. They point to history. The ALH 84001 meteorite from Mars, with its proposed microfossils that many now consider unproven. Early claims of life-related signatures in spectral data that later turned out to be artifacts or misinterpretations. Again and again, desire has run ahead of proof. The lesson is not that we should never make bold interpretations, but that we must recognize how easily our longing for company can color what we see in noisy curves. The skeptics call Fermi's question as another witness, not to cast doubt on life as such, but to remind us that we have seen no clear signs of advanced civilizations. Decades of SETI searches have turned up no repeating beacons, no obvious engineered signals. While this does not weigh heavily on the likelihood of microbial life, it does caution against assuming that the universe is teeming with advanced societies. That, in turn, reinforces their core point. Even if life is common, its more complex and noisy forms might be rare. K218b, if alive at all, is more likely to be home to microbes than to engineers. And microbes leave subtler fingerprints. They also put Webb itself on the stand. Transit signals are tiny. The fraction of light that probes a planet's atmosphere during a transit is minuscule, and the resulting spectral features are small changes riding atop larger variations from the star and the instrument. Assumptions about clouds and hazes, about detector quirks, about stellar spots and flares, all feed into the retrievals. Change those assumptions, and a previously significant molecular identification can fade. The NASA-led reanalysis in July of the year 2025, which found no compelling evidence for dimethyl sulfide even while confirming methane and carbon dioxide, is presented as a key moment. It shows that when a larger, more conservative effort is applied, the most dramatic claim retreats. In their closing remarks, the skeptics do not deny the fascination of K218b. They do not argue that life is impossible there. Instead, they insist on the distinction between not ruled out, plausible, and demonstrated. They remind the court that, so far, no observation has forced us to conclude that biology is the only reasonable explanation. Every supposed biosignature can still be matched by a complex but non-biological model, especially given the incomplete state of our chemical and atmospheric libraries for such exotic conditions. Where does that leave the judge and us? Somewhere in between. The pro-life pillars are real. the quick rise of life on Earth once conditions allowed, the ubiquity of prebiotic organics, the multiple plausible habitats in our own system, the enormous number of habitable zone candidates in the galaxy, and the specific, measured traits of K2-18b's atmosphere. The anti- or weakening pillars are real as well. The lack of clear technosignatures, the ability of abiotic processes to fake biosignatures, the history of false alarms, and the instrumental and modeling limits that complicate every retrieval. As the proceedings adjourn for the day, we look ahead. Webb will continue to observe K2-18b and other promising worlds. Each transit is another hearing, another chance to refine or overturn current interpretations. Next-generation ground-based telescopes with enormous mirrors will join in, able to study certain planets with different techniques. Farther down the timeline, mission planners sketch concepts for space observatories that could directly image Earth-sized planets around nearby stars, separating their light from their suns and spreading it into spectra. A true biosignature machine, an instrument designed from the outset to read the atmospheres of worlds like our own. Beyond even that, there are symbols of how long we have already been leaning toward the idea that someone might be out there. In the late 1970s, two spacecraft called Voyager left the inner solar system on trajectories that will carry them into interstellar space. Each carries a golden record, a phonograph disc encoded with sounds and images of Earth, from greetings in many languages to music and diagrams. It was a gesture both humble and audacious, an acknowledgement that there might be listeners someday, somewhere, who are not us. If we had to issue a verdict tonight, it would be cautious, and it would have two parts. First, the evidence is not yet strong enough to declare that the universe is certainly full of life. We have no unambiguous detection of biology beyond Earth, no spectral pattern so compelling and so thoroughly vetted that alternatives are exhausted. Second, and just as important, it is no longer intellectually honest to say that we are absolutely alone. The combination of what we have learned about chemistry, planets, and atmospheres has moved that stance from prudent skepticism to something closer to denial. We stand, instead, in a wide and complicated middle ground, where the balance of possibilities leans toward a universe that may be alive in many places, even if it has not yet announced itself to us in any voice we can definitively name. If the hallway we are standing in feels unfinished, it is because this is not a story with a clean reveal at the end, only a point where the lights are dim enough that you have to decide how you want to walk the rest of the way. When I look back along the path we have taken, it feels less like a straight line and more like a series of sparks that have gradually lit up the dark. There is the small glass flask in the 1950s where Miller and Urey sent artificial lightning through a mix of gases and found, days later, that simple molecules had woven themselves into amino acids. There is the Murchison meteorite landing in an Australian field and cracking open to reveal that space itself has been busy, quietly building organic complexity in the cold. There are the deep sea vents on Earth, discovered by a submersible's headlights, showing that life does not need sunlight if it has chemical gradients and patience. Then the view pulls outward. We see 51 Pegasi b tugging on its star, the first proof that other suns really do have planets. We see Kepler's crowded diagrams, TRAPPIST-1's 7 small worlds looping tightly around a dim red star, TOI 700d sitting in the soft band where water could flow. And finally, we see the spectra from K2-18b, a set of faint fingerprints in starlight that let us talk, seriously and without laughing at ourselves, about oceans under hydrogen skies and gases that might, or might not yet, hint at biology. With all of that in mind, if I have to lean one way or the other, I lean strongly toward a universe that is full of living places. Not a universe crowded with star-spanning empires or endless versions of us, but one where, whenever rock and water and energy have enough time together, chemistry often finds its way into metabolism. I picture most of that life as microbial, as mats and films and drifting cells. I picture it mostly quiet, without radios or rockets, often hidden under ice, under oceans, under thick atmospheres that never clear enough to see the stars. a cosmos of reefs and soils and vents, rather than a cosmos of cities. That is a worldview choice as much as it is a scientific bet. It is not a claim that advanced aliens are confirmed, or that the lights people see in the sky are visiting craft. It does not depend on any particular story about unidentified objects or secret programs. It is simply the decision to see Earth not as a miraculous exception, but as one more world where the universe has done what the universe seems good at. Taking simple ingredients and, given time, turning them into something that can look back and ask questions. There is a quiet value in that stance. If you let yourself believe that life is probably out there, even in simple forms, then looking at the sky stops being pure observation and becomes, in a small way, a conversation. Every photon of starlight that has passed through the air of a distant planet, every spectrum we take, is a kind of reply. We send out our instruments and our equations. The universe sends back these tiny, patient answers in the shape of absorption lines and temperature curves. We ask, without words, what is happening there? And the light, stripped of certain colors, says, "Here, this is the chemistry I carry." At the same time, honesty demands that we keep our feet on solid ground. The evidence we have is still indirect. It is models and statistics and spectral features pulled from data that sit right at the edge of what our telescopes can resolve. We do not yet have the luxury of photographs of alien microbes, or of ice cores from European oceans, or of biosignature combinations so compelling that no abiotic explanation survives. Until we do, official confirmation will require far more than any single paper or press conference. It will require converging lines of evidence that, together, leave us with no reasonable alternative. Maybe that will happen within our lifetimes. Perhaps a future Webb observation, or a spectrum from one of TRAPPIST-1's planets, or a carefully designed mission that dives through the plumes of Enceladus or samples the regolith of Mars, will reveal a pattern that, after years of attack from every skeptical angle, still stands. Maybe a next-generation space telescope will turn its coronagraph toward a pale dot around a nearby star and see an atmosphere whose gases cannot be arranged by geology alone. Or maybe the universe will keep its secret a little longer, and all we will have are better and better hints, always suggestive, never quite closing the loop. Either way, the choice in front of us now is simple. We can treat the night sky as a ceiling, interesting but mute. Or we can treat it as a set of doors we are slowly learning how to open. If the picture that feels truest to you is the one where life is likely, where K218b and its cousins are more than sterile rocks, then the most meaningful thing you can do is to stay with that uncertainty without rushing to certainty. Pay attention when new data arrive. Let yourself feel the pull of the possible ocean under a red dwarf's dim light. But keep space in your mind for the ways the story might turn. Somewhere, under clouds that reflect a red star's glow, over a deep sea we will never touch, a molecule may be drifting upward from water into air, exhaled by a kind of life whose name we do not yet have. For now, it is only a tiny change in the way a star's light fades as a planet crosses. One day, with better instruments and better questions, we may look at that change and agree, quietly and together, that this is what a living world looks like from far away. Until then, Webb's first knock on the door is still echoing. The invitation is simple. Keep listening, and do not decide too soon how the answer has to sound.